No matter how fast we go, why can't we escape the sun's grip? It isn't a cage, and it isn't visible, yet it holds everything in the solar system tight. The planets, the comets, even the fastest spacecraft we've ever built. The answer lies in the surprising power of gravity. The invisible tug that defines motion, sets the speed we need to break free, and exposes the limits of every rocket humans have ever made. But what if we could push beyond those limits? What if antimatter, fusion drives, or futuristic propulsion could finally let us climb out of the sun's gravitational well? Today, we're exploring why leaving the sun is harder than it seems, and what it could take to truly escape. The sun as a gravity well. Imagine floating in the vast emptiness of space. Stars glimmer in the distance, planets trace their silent arcs around their suns, and comets streak across the darkness on impossibly long journeys. At the center of our own system, the sun sits like a colossal anchor, not just emitting light and heat, but holding the entire solar system in an invisible grip. That grip is gravity, but not just any gravity. The sun's gravity is a force so immense that it warps the very fabric of space around it. To truly understand why we are trapped in its grip, we have to picture something physicists call a gravity well. A gravity well is like a cosmic valley, a depression in the fabric of space-time created by the presence of mass. To imagine it in simple terms, picture a trampoline, stretch it tight. Now place a heavy bowling ball in the center. The trampoline sags under the weight, curving downward. If you roll a marble across the surface, it will inevitably spiral toward the heavy ball, following the curve of the fabric. That's exactly what the sun does to the planets, asteroids, comets, and even light itself. Its immense mass, 1.989 x 1030 kilograms, creates a deep indentation in space-time. Everything nearby moves along the contours of that indentation, unable to escape unless it has extraordinary speed and energy. But unlike a trampoline, space has no edges you can see. Instead, the curvature is invisible, yet it dictates motion across millions of kilometers. The planets of our solar system are never stationary. They are constantly trying to fall into the sun. But here's the delicate balance. They are moving sideways fast enough that as they fall, they also miss it. This is what creates stable orbits, the graceful ellipses traced across billions of kilometers. Earth, for example, is trapped in the sun's gravity well, moving at roughly 30 kilometers per second around it. That speed is fast enough to keep us from plunging straight into the sun, but nowhere near fast enough to escape its grip entirely. Escape velocity is the key concept here. It's the speed an object must reach to break free from a gravitational pull. On Earth, that number is about 11 kilometers per second. Launch a rocket any slower, and it will arc back down to the surface. Launch faster, and it can leave the planet's influence. But the sun is different. Its gravitational well is enormous. From the distance of Earth's orbit, a spacecraft would need to reach nearly 618 kilometers per second to escape the sun completely. To put that in perspective, the fastest human-made object ever, the Parker Solar Probe, will reach speeds of about 192 kilometers per second at its closest approach. That is breathtakingly fast by human standards, yet still not enough to climb entirely out of the sun's gravity well without careful trajectory planning and additional velocity boosts. Imagine trying to climb out of a mountain, not on foot, but with a paper airplane. No matter how strong you throw it at first, the mountain's slopes keep pulling it back. You need precise angles, additional pushes, and sometimes help from external forces like wind currents. In space, the external forces are the gravitational slingshots around other planets. This is why every deep space mission carefully plans flybys of planets like Venus, Earth, Jupiter, or Saturn. Each one can give a spacecraft a boost in speed, helping it climb further out of the sun's well. Without these maneuvers, even our most advanced spacecraft would be stuck orbiting the sun indefinitely. Now, let's zoom in closer. The sun's gravity well isn't a uniform slope. It's dynamic. Its mass is not evenly distributed, solar flares, sunspots, and the turbulent plasma flowing across its surface all subtly change the gravitational landscape. Space around the Sun isn't a smooth trampoline. It's more like a trampoline with shifting weights rolling across it. These shifts are tiny, almost imperceptible across planetary distances, but for precision spacecraft navigation, they matter. The curvature of space around the Sun determines how asteroids drift, how comets swing back into the inner solar system, and how planets maintain their stable orbits over billions of years. Even light is affected. Gravity wells bend light, a phenomenon first confirmed during the famous 1919 solar eclipse by Sir Arthur Eddington. Starlight passing near the Sun didn't travel straight, it curved along the fabric of space-time. This shows that the Sun's gravity is not just a force pulling on mass, it literally warps the arena of space itself. If the Sun were removed, the entire solar system would fly apart, planets drifting off in straight lines at whatever speed they had at that moment. The gravity well is the invisible architecture holding this entire cosmic city together. To really feel the Sun's grip, consider the Oort cloud, a distant shell of icy objects at the edge of the Sun's influence. These objects are tens of thousands of astronomical units away, so far that sunlight takes months to reach them. Yet they remain bound, slowly orbiting a star that seems impossibly far. Even at this extreme distance, the Sun's gravity well dominates, tugging on every object in its reach. Escape is not just hard, it's almost unimaginable. Only an object moving at interstellar speeds can break free, and even then it must navigate the subtle pushes and pulls of nearby stars and galactic tides. The Sun's gravity well is the ultimate cosmic trap. It shapes every orbit, directs every comet, bends light, and holds billions of tons of gas, rock, and ice in its invisible grasp. Every time we look at the planets moving serenely across the night sky, we are witnessing the elegant ballet of bodies dancing on the contours of a deep, invisible well. And yet, despite our most advanced technology, despite our fastest spacecraft, humanity is still tethered. The Sun's gravity well is a masterful cage, and we are prisoners of its invisible chains. Even when we imagine the future, of humanity exploring distant stars, of leaving the solar system entirely, the Sun's gravity well remains the ultimate obstacle. It isn't just a challenge of engineering, it's a challenge written into the fabric of space itself. To climb out, we need not just rockets, but a profound understanding of orbital mechanics, gravity assists, and advanced propulsion methods that can harness the laws of physics rather than fight them blindly. Every maneuver, every slingshot, every ion drive is a step toward escaping the Sun's grip. Yet even the fastest spacecraft must respect the sheer depth of this cosmic well. The Sun as a gravity well is more than a scientific concept. It is a story of scale, of energy, of invisible forces that shape everything around us. It is a reminder that even in the vastness of space, our star dominates, shaping the paths of planets, comets, and humanity's dreams of escape. And as we plan missions that probe closer to the Sun or attempt to break the bonds of the solar system, we are constantly reminded the Sun is not just a light in the sky, it is a master of gravity, the ultimate anchor, and the silent jailer of the planets. Quantifying the Sun's gravity. The Sun's mass is staggering. It weighs in at approximately 1.989 x 1030 kilograms. To put that in perspective, this is more than 330,000 times the mass of the Earth. Every gram of matter on every planet in the solar system combined would barely make a dent compared to the Sun's mass. This enormous mass produces a gravitational pull that dominates the solar system, shaping the motion of planets, moons, asteroids, comets, and even interstellar objects that pass near the Sun. Quantifying this gravity is not just a matter of academic interest. It is the key to understanding why the solar system is structured the way it is, why planets maintain stable orbits, and why leaving this system entirely is so challenging. Gravity is a force that scales directly with mass. The Sun, as the central mass of the solar system, warps the surrounding space in a way that can be measured and calculated. In Newtonian physics, the gravitational force between two objects depends on their masses and the distance between them. The Sun's mass is so large that even at vast distances, its pull dominates over any other influence. For example, at the orbit of Earth, roughly 150 million kilometers from the Sun, its gravitational pull is strong enough to keep Earth in a stable orbit while also dictating the orbital speeds of every other planet. Mercury, the fastest planet, must orbit at nearly 48 kilometers per second to counteract the Sun's pull, while Neptune, orbiting far out at 30 astronomical units, moves at only about 5.4 kilometers per second, perfectly matching the shallower slope of the Sun's gravity well at that distance. The mass of the Sun directly determines the structure of the solar system. Every orbit, from the closest planet to the most distant icy body in the Kuiper belt, is a response to this gravitational anchor. Orbital dynamics are entirely predictable because the Sun's mass dominates the system. Planetary orbits are not random. They follow precise paths determined by the balance between gravitational attraction and the planet's own momentum. Planets are constantly in free fall toward the Sun, but their sideways motion keeps them moving along curved paths instead of colliding with the solar surface. The Sun's gravity sets the speed, shape, and orientation of these orbits. Mercury's rapid orbit, Venus's almost circular path, Earth's stable 365-day orbit, and Neptune's slow sweep across the sky. All of this is a direct consequence of the Sun's immense mass. Gravitational force decreases with distance, following an inverse square law. That means as a planet moves farther from the Sun, the pull diminishes proportionally to the square of the distance. This explains why planets further out move more slowly. Neptune, at the edge of the planetary system, experiences a much weaker pull than Mercury does near the Sun, and its orbital period is about 165 Earth years. The Sun's mass creates a gradient of gravitational strength across the solar system, and this gradient shapes the time each planet takes to orbit the Sun. The balance between distance, speed, and gravitational force creates the harmonious structure of the solar system, and even slight deviations in these factors can lead to dramatic changes in orbital behavior over millions of years. Quantifying the Sun's gravity also allows scientists to calculate escape velocities for different locations within the solar system. Escape velocity is the speed needed to break free from a gravitational pull without further propulsion. At Earth's orbit, the Sun's escape velocity is approximately 618 kilometers per second. No spacecraft has ever reached this speed under its own power. Even the Parker Solar Probe, the fastest human-made object ever, achieves about 192 kilometers per second at its closest approach. These numbers highlight the scale of the Sun's gravitational dominance. Every attempt to leave the solar system must contend with the depth of this gravity well. Planetary flybys, slingshots, and careful trajectory planning are essential to provide incremental velocity boosts needed to climb out of the Sun's influence. The Sun's mass also determines the stability of smaller objects, such as asteroids, comets, and dwarf planets. The Kuiper belt, a region beyond Neptune, contains thousands of icy bodies whose orbits are directly shaped by the Sun's gravity. Even at distances of 50 astronomical units or more, the Sun's gravitational pull is strong enough to keep these objects bound to the solar system. Sedna, a dwarf planet with a highly elongated orbit, takes more than 11,000 years to complete one trip around the Sun. Its motion is governed by the same gravitational principles as Earth's orbit, but on a much larger scale. The Sun's mass is the constant factor that holds all these diverse paths together, ensuring the solar system's coherence over billions of years. Even the Oort cloud, a hypothetical shell of icy bodies at the very edge of the Sun's influence, demonstrates the reach of this gravity. These objects, lying tens of thousands of astronomical units away, are extremely weakly bound, yet the Sun's gravity still holds them in orbit. Their interactions with passing stars or galactic tides can perturb their paths, but the Sun remains the central gravitational anchor. This enormous reach illustrates how the Sun's mass dictates motion across immense distances, far beyond the planets, creating a boundary between objects bound to the solar system and those that truly belong to interstellar space. The Sun's gravity also influences interstellar objects passing through the solar system. When Oumuamua entered our system, its path was altered by the Sun's gravitational field, bending its trajectory without capturing it. The Sun's mass is sufficient to affect the motion of objects coming from light years away, even when they approach at tens of kilometers per second. This shows that the Sun's gravitational pull is not only central to the solar system's internal dynamics, but also serves as a cosmic gatekeeper, shaping how external objects interact with the system. Understanding the Sun's gravity is crucial for space missions. Every spacecraft leaving Earth must first escape our planet's gravity, then navigate the Sun's deeper and more extensive well. Missions like Voyager, New Horizons, and Parker Solar Probe depend on gravity assists from planets to increase velocity efficiently. These maneuvers exploit the Sun's mass indirectly, using the gravitational field of planets that are themselves bound by the Sun to amplify speed and adjust trajectory. The Sun's mass dictates the position and motion of these planets, which in turn determine the possibilities for slingshot maneuvers. Without understanding the Sun's gravitational influence quantitatively, no mission could accurately reach its target or achieve interstellar trajectories. The mass of the Sun also shapes tidal effects on planets and smaller objects. While tidal forces are much stronger near massive, dense bodies like black holes, the Sun's gravity still exerts subtle tidal influences, particularly on comets approaching the inner solar system. These forces can stretch, compress, or even disrupt objects if they pass too close. The Sun's mass is the underlying factor, creating the gravitational gradient responsible for these effects. Even planets like Earth, with relatively strong self-gravity, experience minor tidal forces from the Sun that influence phenomena such as ocean tides and long-term orbital dynamics. Quantifying the Sun's mass allows scientists to calculate these forces with precision, predicting the behavior of objects across the solar system. The Sun's gravity well is dynamic on smaller scales due to solar activity. Variations in the solar wind, coronal mass ejections, and the movement of plasma in the Sun's outer layers create minute changes in gravitational influence. These effects are tiny compared to the total mass, but over time, they can subtly alter spacecraft trajectories or the motion of small solar system bodies. Modern spacecraft navigation accounts for these variations, relying on accurate measurements of the Sun's mass distribution and real-time monitoring of solar activity. The ability to quantify the Sun's gravity to such precision is a cornerstone of modern astrophysics and space exploration. Planetary motion provides the clearest evidence of the Sun's gravitational dominance. Each orbit is a delicate balance between the planet's velocity and the Sun's pull. Small variations in the Sun's mass would have drastic consequences. If the Sun was slightly more massive, inner planets would need to move faster to maintain stable orbits, potentially destabilizing the outer planets. If the Sun were less massive, planets might drift outward, and some could even escape the solar system entirely. The Sun's mass is finely tuned, ensuring that the solar system remains coherent and stable over billions of years. Quantifying this mass is not abstract. It explains the architecture and longevity of the entire system. Comets provide additional examples. Long-period comets originating in the Oort cloud take tens of thousands of years to complete an orbit, yet they remain bound to the Sun despite enormous distances. Their paths are defined by the Sun's mass, with slight perturbations from passing stars occasionally nudging them toward the inner solar system. These comets reveal the Sun's gravitational reach, demonstrating that even the most distant objects in the solar system respond to its pull. Calculating the Sun's mass allows scientists to predict the timing, velocity, and trajectory of these comets with remarkable accuracy, a testament to the central role of gravity in shaping motion. Quantifying the Sun's gravity also explains why spacecraft must follow specific trajectories to reach outer planets or interstellar space. Simply launching in a straight line is insufficient. The Sun's mass dictates the shape of every orbit, including the paths of spacecraft. Gravity assists leverage the mass of planets, which themselves orbit within the Sun's gravitational field, to increase speed without additional fuel. The Sun's mass determines the positions of these planets, and therefore the timing and geometry of the assist. Every mission, from Pioneer to Voyager to New Horizons, relies on the predictable, quantifiable influence of the Sun's gravity to reach targets that would otherwise be unreachable. Even light, which travels at the ultimate speed limit of the universe, is affected by the Sun's mass. Gravitational lensing occurs when light passes near a massive object and bends along the curvature of space-time. The Sun's mass is sufficient to bend starlight, a phenomenon first observed during a solar eclipse in 1919. The measurable deflection of light confirmed both the mass of the Sun and the curvature of space-time it produces. The Sun's gravity is not limited to moving matter. It shapes the motion of energy and radiation, demonstrating the universal scope of its influence. The Sun's mass also provides context for interstellar travel. Reaching another star requires leaving the Sun's gravity well entirely, which demands velocities far beyond what current propulsion can achieve. Even the fastest human-made objects remain bound to the Sun, unless carefully boosted through slingshots and advanced propulsion concepts. The Sun's mass defines the energetic boundary of the solar system, creating a gravitational trap that constrains motion for all objects inside it. Quantifying this mass allows engineers and scientists to plan missions that respect the physical limits imposed by gravity. The escape velocity. Escape velocity is one of the most fundamental concepts in space science. It is the minimum speed an object must achieve to break free from the gravitational pull of a massive body without further propulsion. Unlike simply moving through space, escape velocity represents the threshold at which the kinetic energy of an object is sufficient to overcome the gravitational potential energy of the body it is trying to leave. It is not a speed a rocket can continuously achieve by burning fuel. It is a target velocity that must be reached at a specific distance from the massive object to break free entirely. At Earth, the concept of escape velocity is familiar to anyone studying space travel. A spacecraft or object on or near Earth's surface must reach approximately 11 kilometers per second to overcome Earth's gravity. This value is derived from the planet's mass, roughly 5.97 x 1024 kilograms, and the distance from the center of Earth, approximately 6,371 kilometers. Achieving this speed ensures that the spacecraft will continue moving away from Earth indefinitely if no other forces act on it. Importantly, 11 kilometers per second is significantly faster than any everyday experience. It is roughly 33 times the speed of sound in air. Reaching this velocity is the first step for all interplanetary missions. But it only allows the spacecraft to leave Earth, not the solar system. The Sun, however, presents a far greater challenge. Its escape velocity at the distance of Earth's orbit, about 150 million kilometers from the Sun, is roughly 618 kilometers per second. This is more than 50 times faster than the speed needed to escape Earth. To achieve this velocity, a spacecraft must overcome the Sun's enormous mass, 1.989 x 1030 kilograms, which produces the deepest gravitational well in the solar system. At this speed, an object could break free of the Sun's pull entirely and continue into interstellar space. The energy requirements to reach such velocities are immense. Unlike escaping Earth, which is already challenging with conventional chemical rockets, escaping the Sun entirely requires either extremely advanced propulsion or carefully planned gravitational maneuvers. No current rocket engine can accelerate a spacecraft directly to 618 kilometers per second under its own power. Even the fastest probes ever launched, such as the Parker Solar Probe, approach a maximum of about 192 kilometers per second during close solar passes. While this is astonishingly fast, it still falls far short of the speed needed to escape the Sun from Earth's orbit. As a result, every interstellar probe to date has relied on gravity assists, slingshot maneuvers around planets that themselves orbit within the Sun's gravitational field. These assists allow spacecraft to incrementally gain speed without carrying unfeasibly large amounts of fuel. Each maneuver must be precisely timed and calculated, exploiting the predictable positions and motion of planets to amplify velocity while navigating the contours of the Sun's gravity well. Escape velocity is not a fixed number throughout the solar system. It decreases with distance from the Sun because gravitational pull diminishes with the square of the distance. For example, at the orbit of Jupiter, the escape velocity from the Sun drops to around 220 kilometers per second. At Saturn's orbit, it falls further to approximately 134 kilometers per second. This gradient shapes mission planning. Spacecraft launched toward the outer planets can gradually climb out of the Sun's well with assistance from the planets themselves, effectively stair-stepping their way toward escape. By contrast, any attempt to escape the Sun from the inner solar system requires enormous initial velocity or multiple gravity assists to avoid falling back toward the Sun. The challenge of reaching escape velocity from the Sun illustrates the energy scales involved. Kinetic energy increases with the square of velocity. This means that reaching the Sun's escape velocity from Earth requires more than 50 times the kinetic energy needed to escape Earth itself. Traditional chemical rockets are not energy efficient enough to accomplish this directly. Advanced propulsion concepts such as ion drives, nuclear thermal rockets, fusion propulsion, and even antimatter engines have been proposed to provide the sustained acceleration needed to approach these extreme velocities. Each technology must overcome not only the energy requirement, but also the limitations of spacecraft mass, fuel storage, and heat management. Escape velocity also affects trajectory planning and mission duration. Spacecraft that do not reach sufficient speed remain bound to the Sun, orbiting indefinitely unless assisted. Even objects moving at hundreds of kilometers per second may continue to orbit the Sun on highly elongated elliptical paths rather than escaping. This is why the Voyager probes, despite traveling at remarkable speeds, remain under the Sun's influence. Voyager 1, currently the farthest human-made object from Earth, has been traveling for over 40 years at roughly 17 kilometers per second. It has not yet reached escape velocity from the Sun, and its trajectory continues to be influenced by the Sun's gravity as it moves toward interstellar space. The concept of escape velocity also informs our understanding of interstellar objects. Bodies like Oumuamua and Borisov entered the solar system at speeds sufficient to pass through without being captured by the Sun's gravity. Their trajectories reveal the strength of the Sun's gravitational pull. Objects entering at lower speeds would have been trapped, eventually becoming bound to the Sun in highly elongated orbits. The Sun's escape velocity acts as a threshold, dividing objects that remain in the solar system from those that continue on an unbound path through interstellar space. Human space exploration strategies depend entirely on understanding and exploiting escape velocity. Planetary flybys, carefully timed orbital insertions, and gravity assists are all designed to incrementally increase a spacecraft's speed using the Sun's own gravitational field to our advantage. Without these techniques, escape from the Sun's gravitational well would be impossible. Each planetary flyby from Venus to Jupiter is an intricate dance, transferring energy from the planet's orbital motion to the spacecraft. The Sun's mass ensures that the positions of these planets are predictable, allowing engineers to plan these complex trajectories with high precision. Escape velocity is also critical for considering the future of interstellar travel. Concepts for sending spacecraft to nearby stars, such as Proxima Centauri, rely on velocities far exceeding what current technology can achieve. Even with theoretical propulsion systems, the energy requirements remain dominated by the need to overcome the Sun's gravitational influence. Any interstellar mission must first escape the solar system, making the Sun's escape velocity the primary barrier. Advanced designs consider multi-stage acceleration, laser propulsion, or using the Sun itself as a gravitational slingshot to gain additional speed. In all cases, the calculations begin with the fundamental physics of escape velocity. The physics of escape velocity highlights the scale and challenge of space exploration. It is not a simple speed that can be reached with brute force. It is the threshold at which a body's kinetic energy matches the gravitational binding energy of the massive object it seeks to leave. For Earth, this threshold is already extreme compared to everyday experience. For the Sun, it represents a boundary that current technology can only approach indirectly. Every human-made object attempting to leave the solar system must respect this boundary, gradually accumulating the required energy through clever navigation and gravitational engineering. Even for robotic missions, understanding escape velocity shapes spacecraft design. Propellant mass, thrust capacity, and mission duration all depend on the velocity required to leave the Sun's influence. Missions that aim for the outer solar system or interstellar space must carefully balance spacecraft mass with propulsion efficiency, ensuring that the final velocity approaches or exceeds the Sun's escape threshold. Detailed calculations allow engineers to predict fuel requirements, trajectory corrections, and mission timelines, demonstrating how a fundamental concept like escape velocity underpins every aspect of space exploration planning. Escape velocity also provides context for why the solar system remains gravitationally bound. The planets, moons, and smaller objects are moving at velocities significantly below the Sun's escape velocity at their respective distances. Earth moves at about 30 kilometers per second, Mars at 24 kilometers per second, Jupiter at 13 kilometers per second. None of these speeds are close to the approximately 618 kilometers per second needed to leave the Sun entirely. This ensures that all these objects remain trapped within the Sun's gravitational well, forming a coherent system over billions of years. The Sun's escape velocity is the invisible barrier that maintains this structure, preventing planets from drifting into interstellar space under normal conditions. The magnitude of the Sun's escape velocity also highlights the scale of interstellar distances. Even if a spacecraft could reach 1% of the required speed to escape the Sun from Earth, it would take thousands of years to leave the solar system. Achieving the full escape velocity transforms space travel into an entirely different scale, where time and distance must be considered in centuries or millennia. This reality informs both the design of long-duration missions and the development of theoretical propulsion concepts intended for human or robotic interstellar exploration. Escape velocity is more than a number. It is a measure of the energy required to leave the solar system, a benchmark for the limits of human engineering, and a fundamental property of how mass and gravity interact. For every spacecraft launched, every orbit calculated, and every mission planned, escape velocity is the ultimate reference point. It defines the boundary between being trapped within the Sun's gravitational well and venturing into the uncharted realms of interstellar space. Understanding and calculating escape velocity allows humanity to push the limits of exploration while respecting the laws of physics that govern motion on the larger scale. Historical discoveries and the physics behind it. Long before rockets, before telescopes could pierce the distant reaches of the solar system, humans wondered why planets moved the way they did. The ancients charted the heavens, noting the steady paths of planets, the arc of the sun across the sky, and the patterns of the stars. Yet all of this motion was a mystery, until one mind changed the way we understand the universe forever: Isaac Newton. Newton's insight came from observing apples falling from trees, but his vision went far beyond apples. He realized that the force pulling the apple toward the ground was the same force holding the moon in its orbit around Earth. Gravity, he proposed, was universal. It wasn't just something happening locally on Earth. It governed motion across the cosmos. Every object with mass attracted every other object, and the strength of that attraction depended on their masses and the distance between them. For the first time, the motion of the heavens could be explained with the same laws that explained everyday objects on Earth. Before Newton, planetary motion was described largely through observation and complex geometrical models. like those of Ptolemy or Copernicus. Orbits were calculated, predicted, and refined, but no one truly understood the force behind them. Newton changed that. With his law of universal gravitation, he gave humanity a tool to not only describe motion, but to predict it. He could explain why Earth orbits the Sun instead of shooting off into space, why the Moon doesn't fall straight down, and how the planets stay locked in their paths for billions of years. Newton's laws didn't just describe motion, they predicted it. His second law, that force equals mass times acceleration, combined with universal gravitation, allowed him to calculate the shape of orbits, the speeds necessary for circular or elliptical paths, and even the energy required for an object to escape a gravitational field entirely. It was the birth of what we now call orbital mechanics. These calculations showed that motion in space wasn't chaotic. There was a rhythm, a logic to the cosmos, written into the very mathematics of gravity. Escape velocity, the speed needed to break free from a massive object, was a direct consequence of Newton's work. The same force that keeps Earth in orbit is the same force holding us down. The faster something moves, the less it is pulled back by gravity. Newton's equations showed that if a rocket reaches a certain speed, it can overcome the pull of a planet or the Sun without needing to fight gravity anymore. This was revolutionary. It meant that leaving Earth, or even the solar system, was a question of energy and speed, not of magic or impossible engineering. Newton's physics also predicted subtler effects. Orbits were not perfect circles, they were ellipses. The Sun's mass determined the curvature of each planet's path. Closer planets move faster, distant planets slower. Each orbit is a balance between falling toward the Sun and moving forward fast enough to miss it. Newton described this balance mathematically, and his predictions matched observations with stunning accuracy. Mercury, Venus, Earth, Mars, all followed paths that could be calculated years or even decades in advance. His laws didn't just explain planets, they applied to moons, comets, and artificial objects. When humans finally sent probes into space, engineers relied directly on Newton's formulas to determine how fast a rocket needed to go, when it should fire its engines, and how to use gravity assists to speed along its path. Without Newton, even sending a satellite into orbit would have been guesswork. His work transformed the heavens from a mysterious, untouchable realm into a landscape governed by rules humans could understand, and eventually navigate. Gravity's universality meant that the Sun's pull could be calculated with precision. Using Newton's laws, astronomers could determine how fast a planet had to move to remain in orbit, or how fast a spacecraft needed to travel to leave the solar system. These calculations revealed something profound. Even at vast distances, the Sun's mass dominates. Earth, Jupiter, Neptune, they are all tethered by the same invisible force, and that force is predictable, measurable, and navigable. Newton's work laid the foundation for centuries of exploration. It was the first time humanity could connect the motion of a falling apple, the orbit of the Moon, and the trajectory of distant comets under a single law. Every mission beyond Earth, every probe into deep space, relies on that insight. Escape velocity, orbital mechanics, gravity assists, they all trace their roots back to Newton's genius. Einstein and general relativity. Gravity had always been thought of as a force pulling objects toward each other, a mysterious but predictable influence. Newton had given humanity the equations to calculate it, to predict the motions of planets, moons, and comets, and even to design spacecraft trajectories. But there was still a limit to this understanding. Newton's gravity worked beautifully for most situations, yet it could not explain everything. Small discrepancies in Mercury's orbit, the bending of starlight by the Sun, and the behavior of objects in extremely strong gravitational fields hinted at a deeper truth. And that truth came in 1915, when Albert Einstein unveiled his theory of general relativity. Einstein's insight was revolutionary. Gravity was not just a force, it was a feature of the fabric of the universe itself. space and time were not fixed, static stages where objects moved. They were woven together into a single continuum called space-time, and massive objects could bend and warp this fabric. The Sun, with its enormous mass, doesn't just pull on planets like an invisible hand. It curves the very space around it. Planets move not because they are being pulled in the Newtonian sense, but because they are following the curved paths dictated by this warped space-time. Orbits become natural trajectories along the dips and slopes of this cosmic fabric. The Sun's mass is so great that it creates an exceptionally deep gravity well. A gravity well can be thought of as a valley in space-time. The heavier the object, the deeper and steeper the valley. The Sun's well is the deepest in the solar system. Earth, Mars, Jupiter, all of them move along this valley, never able to escape unless they reach a tremendous speed. Unlike Newton's equations, which describe gravitational pull as a force acting at a distance, Einstein's theory describes it geometrically. Planets orbit because the space around the Sun is curved. In essence, mass tells space-time how to curve, and curved space-time tells mass how to move. This is not a metaphor, it is the way the universe behaves. One of the most dramatic predictions of general relativity is that light itself, which has no mass, can bend around massive objects. Newtonian physics could not account for this. According to Einstein, the Sun's mass curves space-time so severely that even photons, the particles of light, follow the curved paths dictated by this warping. During the solar eclipse of 1919, astronomers traveling to Africa and South America photographed stars near the edge of the Sun. They observed that the starlight was indeed deflected, just as Einstein had predicted. The Sun's gravity well was visible in action, bending the very path of light across the cosmos. Humanity had for the first time witnessed gravity as geometry, not just force. This bending of space-time has practical consequences. Mercury's orbit, for instance, shifts slightly over time in a way Newton's laws couldn't fully explain. Einstein's equations accounted perfectly for the precession of Mercury's perihelion. The planet moves faster when closer to the Sun, slower when farther out, and the Sun's deep gravity well subtly warps its path, creating a cumulative shift over decades. Without the framework of general relativity, these deviations would remain a puzzle. The Sun's curvature of space-time is not a theoretical curiosity, it is a real, measurable phenomenon that governs the motion of planets and spacecraft alike. Even light passing near the Sun on its way to Earth experiences this curvature. Radio signals, laser beams, and even the signals from interplanetary probes must account for the Sun's gravitational bending. Space agencies like NASA routinely factor this effect into navigation calculations. When communicating with distant spacecraft, the time delay and apparent position of signals are affected by the Sun's warping of spacetime. The Sun is more than a source of light and heat. It is a massive lens, bending, stretching, and shaping the paths of anything that comes near it. The Sun's gravity well, in Einstein's terms, is profound. It is not merely a hole in space, but a depression in spacetime itself. Planets are moving along curved geodesics, which are the straightest possible paths in this warped geometry. Orbits are not circles or ellipses in the classical sense. They are trajectories along the contours of a four-dimensional space-time landscape. The Sun's mass defines the depth and steepness of this landscape. A small perturbation, such as the gravitational influence of another planet, can slightly shift a path, but the Sun's dominant mass ensures that the valley remains the controlling feature. Even comets traveling thousands of astronomical units away are bound by this curvature, tethered to the Sun's gravity well. Einstein's equations also revealed that the Sun's gravity well affects time itself. Clocks closer to massive objects run slightly slower than clocks farther away. This phenomenon, called gravitational time dilation, is measurable on Earth in satellites orbiting our planet, and is even more pronounced closer to the Sun. Time does not flow uniformly, it is stretched and warped by the Sun's mass. A spacecraft approaching the Sun experiences time differently than one at the outer edges of the solar system. This is not science fiction, It is a consequence of the Sun's gravity warping both space and time, a reminder that general relativity is a theory of the fabric of reality itself. The Sun's gravity well also gives rise to phenomena like gravitational lensing on cosmic scales. Massive stars bend light from background objects, creating arcs and multiple images of the same star or galaxy. While the Sun is small compared to these cosmic giants, it demonstrates the principle perfectly. During eclipses, the Sun provides humanity with the first visible proof that space-time is curved, a demonstration of how mass shapes the universe. Einstein's insights transformed our understanding. The Sun is not just a glowing star, it is a sculptor of the cosmic stage, warping space and time with its immense mass. These concepts are critical for modern space exploration. Every interplanetary mission must navigate a universe shaped by Einsteinian physics. A trajectory calculated purely with Newtonian mechanics will be slightly off. Spacecraft passing close to the Sun, such as the Parker Solar Probe, experience tiny shifts in velocity and trajectory because of the Sun's curved space-time. Mission planners incorporate relativistic corrections to ensure precise navigation. Even small errors accumulate over millions of kilometers, which can mean missing a planet by thousands of kilometers if Einstein's corrections are ignored. The Sun's mass and its gravity well are the invisible architects of every successful journey through the solar system. Einstein's theory also reframes the concept of escape velocity. In Newtonian terms, it is the speed needed to overcome a gravitational pull. In relativity, it is the speed at which an object can leave a curved region of space-time. The deeper the well, the closer you are to the Sun, the more energy is required to escape. Near the Sun's surface, this energy is enormous. Spacecraft leaving Earth are already climbing out of two wells, the Earth's and the Sun's. Relativity refines this understanding, showing how space and time stretch and curve along the escape path. For missions venturing close to the Sun, like the Parker Solar Probe, these relativistic effects are measurable and critical for trajectory planning. The Sun's curvature of space-time also sets a fundamental limit. The Sun's gravity well is so deep that even light is bound unless it passes beyond the surface of the Sun's well at a sufficient distance. This is why the Sun casts shadows and why solar photons eventually escape, but at precisely defined trajectories. The Sun is a natural laboratory for general relativity. Its proximity allows us to measure subtle effects that in other stars would be imperceptible. The bending of light, the precession of planetary orbits, and the influence on spacecraft trajectories all demonstrate how the Sun's mass warps the universe around it. Einstein's general relativity transformed our understanding of the Sun from a massive ball of gas into a dynamic feature of space-time. Newton's laws were local and force-based. Einstein's laws are geometric and universal. The Sun creates a depression in the fabric of reality itself, a deep three-dimensional valley that dictates how everything nearby moves. From Mercury's orbit to Earth's path, from comets to interstellar visitors, nothing escapes the influence of this curved space-time. Even the speed of light, the ultimate cosmic speed limit, is shaped by this well. This understanding opens up the next frontier. If the Sun's mass can warp space-time so profoundly, what happens with even denser objects? Black holes, neutron stars, and other massive cosmic entities produce wells so deep that not even light escapes. But here, in our own solar system, the Sun is the giant anchor, the ruler of the local space-time, the entity whose mass bends the universe around us. Every orbit we track, every spacecraft we launch, every ray of sunlight that reaches Earth, all are defined by the curvature of space-time that Einstein described a century ago. Modern observations. The Sun is not just a glowing ball in the sky. It's a living, dynamic force, and today we have the tools to see it like never before. Modern science doesn't just theorize about its gravity. It measures, tests, and even rides along with it. And nothing brings that home more than the daring journeys of solar probes. Take the Parker Solar Probe. Launched in 2018, this tiny craft with its heat-shielded body is diving closer to the Sun than anything humanity has ever sent. It's not just flying past, it's plunging into the outer layers of the solar atmosphere, skimming the corona at blistering speeds. Here, the Sun's gravity is brutal, tugging at the spacecraft with a force millions of times stronger than what we feel on Earth. Parker's mission is a direct test of everything we know about the Sun's pull. Every maneuver, every orbit, every trajectory correction is calculated to account for the Sun's mass and the curvature of space-time. As Parker swoops through the solar corona, it records the solar wind, the streams of charged particles blasting from the Sun. These winds are shaped by the Sun's gravity well, guided along paths dictated by the warping of space-time. By measuring their speed, density, and direction, scientists can see how the Sun's gravity organizes matter even in its outermost regions. These data also reveal subtle shifts in the spacecraft's path, tiny tugs from the Sun that are a live demonstration of gravity in action. Every measurement Parker takes is a real-world confirmation of the same physics Einstein predicted over a century ago. But solar probes aren't the only evidence. Every planetary mission we've launched has to dance with the Sun's pull. Whether it's Juno orbiting Jupiter, Cassini around Saturn, or New Horizons speeding past Pluto, each spacecraft must account for the Sun's gravitational grip. Early missions like Voyager relied heavily on gravity assists, essentially slingshotting around planets to steal speed from their motion around the Sun. These maneuvers only work because the Sun's position, mass, and pull are precisely known. One tiny miscalculation, and a spacecraft could miss its target by thousands of kilometers. The precision of these missions is astonishing. Take New Horizons, for example. After its historic flyby of Pluto, it continued outward into the Kuiper Belt, traveling billions of kilometers. Throughout its journey, every adjustment to its trajectory accounted for the Sun's gravity. Even at extreme distances, where the pull is weaker, it is still the dominant force shaping the spacecraft's path. Nothing else in the solar system, no planet, no comet, exerts enough influence to override the Sun. Modern observations show that the Sun's gravity well extends far beyond what we might intuitively imagine, holding even distant icy bodies in place and directing the movement of our robotic explorers. Even small corrections reveal the Sun's influence. Radio signals from interplanetary spacecraft sometimes arrive slightly off-time or shifted in frequency because the Sun's gravitational field bends the path of the signals and slows time near the Sun. Engineers factor in these relativistic effects to keep communication precise. It's not just theory. It's a measurable, tangible effect. The Sun is bending reality itself, and every modern observation confirms it. Modern telescopes and tracking systems extend this observation beyond spacecraft. By charting asteroid paths, comet orbits, and even distant Kuiper Belt objects, scientists see the Sun's gravitational fingerprint everywhere. Objects that appear to wander freely are still subtly tethered. Long-period comets, taking tens of thousands of years to swing around the Sun, are effectively prisoners of this massive gravity well. The Sun's pull dictates the timing, shape, and speed of every orbit, from the fastest inner planets to the slowest distant bodies. Even the fastest spacecraft we've built demonstrate the challenge. The Parker Solar Probe, during its closest approaches, reaches speeds of nearly 700,000 kilometers per hour, blazing fast, yet still carefully choreographed to navigate the Sun's pull. Voyager 1, currently in interstellar space, is moving at tens of kilometers per second, faster than any planet. Yet it too was constrained for decades by the Sun's gravity, using planetary assists to gradually climb out of the well. These missions are practical proof that escaping the Sun's gravity is not just a theoretical exercise, it's a monumental engineering challenge. Modern observations also reveal the dynamic side of the Sun's gravity. It's not a uniform, unchanging field. Solar flares, coronal mass ejections, and shifting magnetic fields create local perturbations that subtly affect objects passing nearby. Even a spacecraft on a carefully plotted trajectory can experience tiny nudges from these solar events, requiring constant adjustment. This is gravity in action, alive and interactive, not just a static pull. The Sun is a living anchor, shaping motion across the solar system in real time. Gravity also influences the distribution of matter in the inner solar system. Observations of near-Earth asteroids, comets, and dust reveal paths shaped by the Sun's pull. Objects spiral inward, drift outward, or get trapped in resonances with planets because of the Sun's mass. Spacecraft studying these populations, like OSIRIS-REx at asteroid Bennu, must account for these subtle gravitational effects to approach, orbit, and return samples safely. Even microgravity, the tiny pull experienced by spacecraft in orbit, is a reminder of the Sun's far-reaching influence. What's striking about modern observations is the precision with which we can now measure the Sun's gravity. Centimeters matter. Tiny deviations in spacecraft velocity or orbit reveal the curvature of space-time itself. Relativistic corrections aren't theoretical, they're implemented in every mission planning system. GPS satellites around Earth even rely on these corrections because Earth's gravity warps time, and the Sun's presence adds an additional layer. The Sun is not distant or abstract. Its pull is woven into every trajectory, every calculation, every path we trace through the solar system. Even light isn't immune. Solar eclipses allow astronomers to observe starlight bending around the Sun, confirming Einstein's predictions. Modern instruments can measure this effect with unprecedented accuracy, using radio waves or optical telescopes to track light paths near the Sun. Each observation reinforces what our probes feel directly. The Sun's mass curves everything around it, from spacecraft to photons. The solar system as a cosmic trap. The solar system is a prison, but not in the sense of walls, bars, or chains. It is a trap built entirely by gravity and motion, a delicate, invisible structure sculpted by the Sun's enormous mass. Every planet, moon, asteroid, and comet is caught in this trap, confined to paths dictated by forces so vast that human imagination struggles to grasp them. These paths are not random. They are precise, predictable, and eternal, defined by the interaction between the Sun's gravity and each object's own momentum. From a distance, planetary orbits might appear as simple circles drawn on a cosmic blackboard. But they are not circles. They are ellipses, slightly stretched, slightly skewed paths that planets follow as they fall around the Sun without ever hitting it. Newton's laws explained this beautifully. A planet is constantly falling toward the Sun, but it is also moving forward. This forward motion, called orbital momentum, counterbalances the pull of the Sun's gravity. The result is a perpetual dance. The planet falls, but never lands, moving in a path that curves endlessly around the central star. Earth, Mars, Venus, and all the planets are moving along these invisible tracks, forever confined by the balance of pull and motion. Every planet's orbit is a delicate equilibrium. Too slow, and gravity would win. The planet would spiral inward, drawn into the Sun, crushed by its heat and mass. Too fast, and the planet would break free, shooting into interstellar space, never to return. This balance is exact. Earth moves around the Sun at roughly 30 kilometers per second, fast enough to avoid falling in, slow enough to avoid flying away. The Sun's gravity exerts an invisible leash, holding the planets in check. This is why the solar system works like clockwork, with each planet in a stable orbit, year after year, century after century. Elliptical orbits add another layer of complexity. Unlike perfect circles, these ellipses have a closest point to the Sun, called perihelion, and a farthest point called aphelion. Earth's orbit is slightly elliptical, bringing it closer to the Sun in January and farther away in July. Mercury, being closest to the Sun, has a more stretched orbit, swinging fast when near perihelion and slower when farther away. This stretching is a direct consequence of gravitational physics. As the Sun tugs harder on a planet when it's close, the planet speeds up. As the tug weakens farther out, the planet slows down. Each orbit is a continuous exchange of energy between the Sun's pull and the planet's motion, a cosmic seesaw that traps planets in repeating paths. Even moons follow this pattern. Jupiter's moons, Saturn's rings, and the smaller moons of Mars all obey the same rules. Gravity tethers them to their planets, which are themselves tethers to the Sun. These nested orbits are mini-traps within the larger Sun-centered trap. A moon cannot escape its planet without gaining enormous speed, and a planet cannot escape the Sun without achieving the monumental escape velocity dictated by its distance from the star. The entire solar system is layered like a Russian doll of gravitational wells, each body locked in motion by the balance of pull and speed. Orbital momentum is key to this cosmic trap. It is the energy that resists the Sun's pull. Every planet has a specific amount of momentum, determined by its mass and velocity, which keeps it from falling inward. At the same time, gravity constantly acts to bend the planet's path, maintaining the elliptical orbit. Without this balance, the solar system would collapse or fly apart. The precise measurements of these orbital velocities are stunning. Venus moves at about 35 kilometers per second, Mercury at 48, and Neptune barely 5.5. Each velocity is perfectly tuned to its distance from the Sun, showing the incredible precision of the Sun's gravitational control. Small variations in these velocities or in gravitational forces can have massive consequences. Comets and asteroids that drift too close to a planet can be redirected, sent into new orbits, or even flung out of the solar system entirely. Planetary resonances, where orbits synchronize in exact ratios, create regions of stability and instability. Jupiter, with its massive gravity, shepherds asteroids in the asteroid belt, creating gaps where objects cannot remain for long. Saturn's moons lock into orbital dances that prevent collisions. Every motion is a negotiation between mass, gravity, and momentum, creating a self-organizing trap that spans billions of kilometers. Even distant objects like Pluto or the faraway icy bodies in the Kuiper belt are bound by the Sun's influence. At first glance, these orbits seem loose, almost chaotic, with eccentric shapes and inclined planes. But even here, the Sun's mass dominates. A planet or dwarf planet cannot escape unless it reaches the astronomical speeds dictated by escape velocity. The Sun's gravitational well extends so far that, even at the edge of the solar system, objects are still tethered, slowly orbiting, trapped in the Sun's invisible grip. Modern observations have confirmed just how precise this trap is. Spacecraft like Voyager, New Horizons, and the Parker Solar Probe must carefully navigate the Sun's gravitational influence. Engineers plot every trajectory with incredible accuracy because even a tiny deviation could send a spacecraft off course by millions of kilometers. Gravity assists, such as slingshots around Jupiter or Venus, exploit the Sun's pull, accelerating spacecraft without extra fuel. These maneuvers work because planetary orbits and velocities are predictable within the Sun's trap. Every mission is a live demonstration of the Sun's massive influence, showing that no object can move freely without accounting for its gravitational rules. Even the solar wind, the constant stream of particles from the Sun, is shaped by this trap. Charged particles flow along paths influenced by the Sun's mass and magnetic field. Observations from Parker Solar Probe show that these particles are accelerated, bent, and sometimes captured by the Sun's gravity, spiraling in patterns that echo the larger motions of planets and moons. The Sun's gravity well doesn't just control solid bodies. It shapes the movement of gas, plasma, and even light itself, holding the solar system together in a complex, dynamic trap. The deeper a planet is in the Sun's gravitational well, the stronger the tether. Mercury, being closest, experiences a pull so strong that its orbit precesses slightly over time, an effect that Newtonian mechanics could not fully explain, but which Einstein's relativity accounted for. Earth, farther out, feels a gentler tug, but it is still bound firmly in its path. Even Pluto, orbiting at the outer edge of the solar system, moves slowly but remains tethered. No planet, no moon, no comet can casually drift away. The Sun's gravity is inescapable without massive energy input. Gravity also creates regions of relative stability and chaos. The asteroid belt, Jupiter's Trojan asteroids, and Neptune's resonant Kuiper belt objects all reveal the Sun's sculpting power. These regions exist because of the delicate balance between gravitational pull and orbital momentum. In some areas, the Sun's gravity traps objects in long-term stability. In others, tiny nudges accumulate, sending objects into new orbits, or even ejecting them from the solar system. The Sun's influence is universal. It governs stability, chaos, speed, and path, forming a cosmic prison without walls. Every orbit in the solar system is a negotiation with the Sun's mass. The deeper the orbit, the faster the planet must move to avoid falling in. The farther out, the slower the planet can orbit while still remaining trapped. This balance defines everything: the length of a year, the seasons, the climate, and even the motion of moons and satellites. The solar system functions because the Sun's gravity and planetary momentum are perfectly tuned, forming a system where every motion is predictable yet dynamic, free to move only within the confines of the Sun's invisible leash. Even human technology is bound by this trap. Satellites, space stations, interplanetary probes, all must follow the rules set by the Sun's gravitational field. Launch windows, orbital insertions, and flybys all depend on timing relative to the Sun's influence. Every course correction, every velocity adjustment, every trajectory calculation is a direct interaction with the Sun's mass, showing that humans, too, are operating inside this vast cosmic trap. The Sun's gravity well is also a dynamic stage for collisions, captures, and near misses. Comets entering the inner solar system are stretched, heated, and sometimes fragmented by gravitational forces. Asteroids can be nudged into the inner solar system by Jupiter's gravity, creating the potential for Earth-crossing paths. Even these seemingly chaotic events are bound by the rules of gravity and orbital momentum. There is no random escape. The Sun's mass ensures that everything is either trapped or carefully redirected along paths dictated by its enormous pull. Over billions of years, this trap has shaped the solar system. Planets formed in the protoplanetary disk and settled into stable orbits. Gravity cleared gaps, created belts, and defined the locations of gas giants and terrestrial planets. Today, the trap is fully realized. The Sun holds its family in place, creating a cosmic system that is stable yet alive with motion. Moons, rings, asteroids, and comets all trace paths governed by the interplay of gravity and momentum. Even interstellar objects passing through, like Oumuamua, must enter at high enough speeds to resist being captured. Otherwise, they too would become prisoners of the Sun's trap. The Sun's gravity is relentless. It extends far beyond Pluto, far beyond the Kuiper belt, and even influences objects in the Oort cloud, tens of thousands of astronomical units away. Objects here move slowly, influenced not just by the Sun, but by passing stars and galactic tides. Yet the Sun remains the anchor, the primary force holding them in place. Escape requires enormous energy, far beyond what chemical rockets or even current propulsion technology can provide. The solar system is a natural prison, and the Sun is the warden. Comets, asteroids, and Kuiper belt objects trapped at the edge of the Sun's reach. Beyond the orbits of Neptune and the familiar planets lies a region filled with icy bodies, rocks, and remnants from the formation of the solar system. This is the Kuiper belt, a distant, frigid frontier where sunlight barely warms the surface and where time seems to stretch differently. These objects are far from Earth, yet even here, the Sun's gravity holds sway. The pull is weaker than it is near Jupiter or Saturn, but it is persistent. Every comet, asteroid, and Kuiper belt object, KBO, is tethered, moving along paths dictated by the invisible reach of the Sun's mass. Take Sedna, for example. Discovered in 2003, Sedna's orbit is extreme. Its closest approach to the Sun, the perihelion, is roughly 76 astronomical units, AU, more than twice the distance to Pluto. Its farthest point stretches beyond 900 AU, At first glance, one might think an object this far out could wander freely, drifting into interstellar space. But Sedna is still a prisoner of the Sun's gravity. Its long, elongated orbit is a slow-motion dance, taking thousands of years to complete a single circuit. Even in the cold reaches of the solar system, Sedna cannot escape. The Sun's gravity ensures that despite its vast distance, it remains tethered, moving along the invisible contours of a deep gravitational well. Objects like Sedna demonstrate the remarkable reach of the Sun's influence. Gravity weakens with distance, but it does not vanish. Even in the outer Kuiper belt, the Sun dominates the motion of small, icy worlds, keeping them bound and guiding their paths. These objects are not static. They are in motion, orbiting the Sun in silent, ghostly trajectories, shaped by forces that humans cannot feel, but can calculate with extraordinary precision. Every orbit is a story of balance, the outward inertia of the object versus the inward pull of gravity. Asteroids in the inner solar system tell a similar story on a smaller scale. The asteroid belt, located between Mars and Jupiter, is full of rocks moving at tens of kilometers per second. Each asteroid follows its own elliptical path, shaped not only by the Sun, but also by Jupiter's enormous gravity. Some orbits are chaotic, influenced by resonances that create gaps in the belt, like the Kirkwood gaps, where no stable orbits exist. Even in these areas of apparent instability, the Sun's gravitational reach is evident. Asteroids do not drift off randomly. They are confined within zones determined by the Sun's mass and the gravitational tugs of neighboring planets. Comets add drama to this cosmic story. Long-period comets, originating from the distant Oort cloud, can take hundreds of thousands of years to orbit the Sun. They move slowly at first, far from the Sun, barely influenced by its pull. But as they descend into the inner solar system, gravity tugs more strongly, accelerating them to incredible speeds. Comets like Halley or Hale-Bopp swing around the Sun on breathtaking elliptical trajectories, flaring with heat and activity as ices sublimate under intense sunlight. Even as they streak close to the Sun at hundreds of kilometers per second, they remain on a tethered path. To escape entirely would require energy far beyond natural processes or even human propulsion. Then there are interstellar visitors, objects that challenge the notion of the solar system as a closed trap. Oumuamua, detected in 2017, was the first known interstellar object to pass through our system. Its speed and trajectory showed it was not bound to the Sun. It was a near escapee, gliding past the Sun and planets, moving too fast to be captured. Yet even in its fleeting visit, the Sun's gravity affected its path. Its trajectory bent slightly, a small but measurable deflection caused by the Sun's mass. Oumuamua was free, but the Sun left its mark. The encounter offered a glimpse of the boundaries of this gravitational trap, a fleeting moment where an object approached the Sun's sphere of influence but was not captured. Most comets and KBOs do not get this close to escaping. Pluto, Eris, Makemake, and countless smaller Kuiper belt objects remain confined, following predictable yet astonishingly varied orbits. Their paths can be stretched, tilted, and elongated, but the Sun's pull keeps them moving in loops that repeat over millennia. Even extreme orbits like Sedna's eventually bring these objects back toward the Sun. There is no permanent freedom at these distances. The solar system's outer reaches are a slow-motion trap, governed by the invisible hand of gravity. Interactions among these objects add complexity. Occasionally, comets pass near planets or each other, and small gravitational nudges can alter their orbits. Some are perturbed inward toward the Sun, becoming new members of the short-period comet population, completing orbits in decades instead of millennia. Others are nudged outward, but still remain bound. Occasionally, an object is redirected into an orbit that takes it hundreds of AU from the Sun, but even here, the gravitational leash holds. The Sun's mass is dominant, shaping not only the paths of planets but also the movement of distant icy wanderers. Kuiper belt objects, though cold and distant, reveal the Sun's organizing power on a large scale. Their collective orbits suggest an unseen architecture. Some KBOs cluster in space, their positions hinting at the influence of a massive unseen object, possibly a Planet 9. Whether true or not, this clustering demonstrates that the Sun's gravity, in combination with orbital momentum and resonances, creates subtle patterns even in the farthest reaches. These objects are not scattered randomly. They are confined, trapped, and directed by the Sun's mass. Gravity shapes their destiny, stretching out into the emptiest regions of the solar system. Even when objects attempt near escapes, they rarely succeed. Consider long-period comets like C2013, a one-siding spring which passed close to Mars. Its path was influenced by the Sun and planets alike. Gravity pulled and twisted its orbit, subtly redirecting its trajectory. While these comets may approach the edges of the solar system, they are still part of the Sun's gravitational story. Only with a combination of extraordinary speed and interstellar conditions, like Oumuamua, can an object truly evade capture. The Sun's gravity also affects the shape and timing of these orbits. Objects in the Kuiper belt do not move at constant speeds. They accelerate when closer to the Sun and slow as they retreat. These variations follow precise physical rules, and careful observation shows that even tiny forces can accumulate over time, altering trajectories subtly. The Sun's influence is persistent, reaching across billions of kilometers, bending paths, and dictating motion. Nothing moves freely. Even at the edge of the solar system, inertia is not enough to escape the central star's pull. Asteroids and KBOs are also subject to gravitational interactions with one another, but the Sun remains the primary authority. Collisions are rare, but the collective gravity of the Sun and planets organizes regions of stability and instability. Resonances, gaps, and clusters are all part of this cosmic choreography. Some objects may temporarily escape from one orbit to another, but their motion remains bound within the Sun's trap. Even extreme cases, like Sedna, demonstrate that total freedom is almost impossible without extraordinary energy. Every discovery reinforces this. The distant dwarf planet Eris follows a highly elliptical path, moving from just outside Pluto's orbit to far beyond 100 AU. Yet even Eris is bound, following the invisible curves of the Sun's gravity well. Observations of smaller KBOs reveal elongated orbits that echo the shape of the central gravitational pull. The solar system is not a random cloud of distant bodies. It is an organized, intricate trap. Each icy rock, comet, and dwarf planet moves along a path dictated by the Sun's mass and the laws of motion. Even when new objects are discovered entering the inner solar system, their journeys are influenced by the Sun's reach. Comets accelerated inward by Jupiter's gravity still bend under the Sun's pull. Their speed increases as they near perihelion, and they slow as they retreat. The gravitational well extends its influence over every motion, every orbit, and every passage. This tethering defines the structure of the solar system from the inner planets to the farthest KBOs. Interstellar visitors are rare exceptions, but their paths are shaped as they pass. Oumuamua's speed carried it beyond capture, yet the Sun's gravity bent its trajectory. Observations of future interstellar objects will reveal similar interactions. The Sun's mass acts as a cosmic lens, subtly altering the motion of objects passing nearby. Even fleeting encounters demonstrate the Sun's gravitational dominance and the difficulty of true escape. Every orbit, every path, every comet, asteroid, and KBO illustrates the immense scale of the Sun's influence. Gravity stretches billions of kilometers, holding icy worlds, rocky fragments, and celestial wanderers in invisible chains. Escape is possible only with extraordinary energy, velocity, or interstellar conditions. The solar system is not empty space. It is a finely tuned, gravity-bound system where even distant objects are tethered, trapped in the Sun's cosmic grip. The Oort cloud, the Sun's farthest frontier. Far beyond the familiar planets, beyond Neptune and the scattered objects of the Kuiper belt, lies a region of space almost entirely unknown, stretching tens of thousands of astronomical units from the Sun. This is the Oort cloud, a vast spherical shell of icy bodies, comets, and frozen remnants from the early solar system. It is the outermost boundary of the Sun's gravitational influence, the final frontier where the Sun's pull is faint, yet unrelenting. Even here, in the coldest and most distant reaches, the Sun's gravity traps these objects, holding them in a slow-motion orbit over millennia. The Oort cloud is enormous, potentially extending from 2000 AU all the way to 100,000 AU. To put that in perspective, that is almost halfway to the nearest star, Proxima Centauri. The objects within it are tiny and scattered, often less than a few kilometers across, made mostly of rock, ice, and frozen gases. They move slowly, hardly noticing the warmth of the Sun's light, drifting in elliptical orbits that can take millions of years to complete a single trip around their parent star. Yet despite their distance and isolation, they remain bound to the Sun. The gravitational reach of our star is vast, stretching far beyond what the naked eye can see, or even what most telescopes can detect. Gravity here is weak but persistent. In the inner solar system, gravity pulls strongly, bending the paths of planets and comets with ease. But in the Oort cloud, the Sun's pull is subtle, almost a whisper across the void. These icy bodies drift slowly, and even a small push from a passing star or the tidal forces of the Milky Way can slightly alter their paths. Yet they do not escape. Their orbits may be stretched into extreme ellipses, tilted at odd angles, but they remain part of the Sun's system, tethered by its mass across unimaginable distances. The Oort cloud is believed to be the origin of long-period comets. These are the comets with orbits lasting tens or hundreds of thousands of years. Occasionally, gravitational nudges from a passing star or galactic tidal forces perturb an object in the Oort cloud. This tiny push sends it inward toward the Sun. As it travels, the Sun's gravity accelerates it, drawing it closer with increasing speed. By the time it reaches the inner solar system, it may be traveling at hundreds of kilometers per second, flaring as its ices sublimate under intense sunlight. Even comets that approach the planets for the first time in human history were once distant members of this cold, faraway swarm, held loosely by the Sun's extended gravitational reach. The objects of the Oort cloud are difficult to observe. They are faint, icy, and far from the Sun's warmth. Direct imaging is nearly impossible with current technology. Scientists infer their presence through the comets that occasionally appear, tracing their paths back to these distant origins. Each comet's trajectory tells a story of release from a nearly invisible tether, a slow spiral from the Sun's outer grip into the inner solar system. Without the Sun's gravity, these objects would drift into interstellar space, lost forever. Instead, they remain prisoners in a cosmic dance that stretches for tens of thousands of AU, moving almost imperceptibly through the void. The spherical distribution of the Oort cloud is unique. Unlike the Kuiper belt, which lies roughly in the plane of the planets, the Oort cloud forms a nearly complete shell around the Sun. This shape suggests that the objects were scattered early in the solar system's history, flung outward by interactions with the giant planets. The gravitational tugs of Jupiter, Saturn, Uranus, and Neptune sent icy bodies spinning into distant orbits, forming the loosely bound cloud that now envelops the solar system. Yet no matter how far they travel, they remain tethered. The Sun's gravity, though faint, defines the boundary between the known solar system and interstellar space. Occasionally, objects in the Oort cloud experience close encounters with other stars. The Sun itself is moving through the galaxy, passing near other stars over millions of years. These encounters can slightly alter orbits, nudging objects toward the inner solar system or stretching their paths into even more extreme ellipses. Yet even these interactions cannot completely free objects from the Sun's pull unless they receive extraordinary energy. Most icy bodies continue their slow, almost imperceptible drift, bound to the star at the center of the solar system by a gravity that is subtle but inescapable. The distance of these objects from the Sun means that time operates differently for their orbits. A single trip around the Sun can take 1 million years or more. These are not orbits that humans can easily observe. They are ancient, slow-motion journeys shaped by forces that are invisible, yet undeniable. A body in the Oort cloud may travel closer or farther from the Sun in a cycle that spans the rise and fall of civilizations, yet it never leaves the Sun's influence. Every icy rock is moving within a well-defined gravitational boundary, a prisoner of the star that formed it billions of years ago. Some objects in the Oort cloud may wander toward the planets only rarely. When a comet is nudged inward, it becomes visible from Earth, sometimes for the first time in recorded history. The path it follows is entirely dictated by the Sun's gravitational influence. Even if it swings around the Sun and is sent back outward, it returns to the distant shell, completing a circuit that may take hundreds of thousands of years. Each passage is a fleeting visit to the inner solar system, a reminder that the Oort cloud is not empty space, but a far-reaching arm of the Sun's trap, stretching into the darkness. The weak gravitational binding in the Oort cloud also allows for rare interactions with interstellar objects. Just as Oumuamua passed through the solar system without being captured, other interstellar travelers may come close, their trajectories influenced by the Sun's gravity, but not trapped by it. Occasionally, a passing star may perturb an Oort cloud object enough to eject it into interstellar space, but these events are rare. For most of the icy bodies, the Sun remains the anchor, the invisible tether holding them in place across immense distances. The Oort cloud is enormous in scale. Even the closest parts are thousands of times farther than the Earth-Sun distance. The sheer volume of space it occupies is difficult to comprehend. Yet within this vast expanse, the Sun's gravity rules. It is the central force shaping motion, the constant presence that prevents objects from wandering freely into the galaxy. The icy bodies move slowly, almost frozen in time, yet they are forever bound to a star billions of kilometers away. Gravity here is subtle, but it is precise. The Sun's mass extends its influence so far that every object's orbit, every drift, and every potential trajectory is constrained. The motions are predictable in theory, even if they are nearly impossible to measure directly. Modern simulations allow scientists to model the orbits of millions of hypothetical Oort cloud objects, revealing the structure of this immense outer shell and the Sun's influence over it. These models show that the Sun's gravitational pull continues to organize and shape motion even at distances where the pull is weaker than a whisper. Some Oort cloud objects have orbits that take them closer to the inner solar system for the first time in billions of years. When this happens, they encounter the stronger gravitational fields of the planets, especially Jupiter and Saturn, which can further alter their paths. Yet the Sun's gravity remains the dominant force. Even as planets tug and redirect them, the objects remain within the solar system's outer boundary. Their journeys are long, slow, and dictated by a gravitational grip that is invisible but absolute. The Sun's reach in the Oort cloud is a testament to its mass. It is not merely a source of light and heat, but a force that extends tens of thousands of AU into the void. Comets, icy rocks, and small celestial bodies are all bound, moving in trajectories that are incredibly slow, yet fully controlled by the Sun's influence. Even at the edges of the solar system, where gravity is nearly imperceptible, the Sun's pull continues to dictate motion, creating a trap that is both immense and delicate. Objects in the Oort cloud can remain in these orbits for billions of years. They are remnants of the early solar system, preserved in the cold darkness, traveling along paths set long before Earth even existed. They are a frozen archive of the Sun's formation, held in place by the star's gravity, a system-wide tether that extends to the limits of human imagination. The Sun's gravity, even at this extreme distance, is enough to shape the distribution, paths, and behavior of these icy bodies. Even the tiniest perturbation, a passing star, a molecular cloud, or a galactic tide, can slightly shift an Oort cloud object. Yet, these shifts rarely lead to escape. The sun's pull, though faint, is constant. The Oort cloud is a ghostly, distant reminder that the solar system is not just planets and moons, but a vast, layered gravitational trap. Every object within it, from the smallest ice fragment to the largest comet, is bound to the sun, moving along paths dictated by forces beyond direct perception. Some simulations suggest that the sun may have captured objects from other stars early in the solar system's history. These captured bodies would join the Oort cloud, trapped by the same weak gravity that binds native objects. Even foreign objects become part of the solar system's outer shell, held in a slow-motion orbit around the sun. This shows the reach of the sun's influence, extending even to interactions beyond the solar system itself. The Oort cloud also serves as a source of mystery and discovery. Every comet discovered with a long-period orbit offers a glimpse into this distant region. Scientists trace their paths back to these frozen bodies, reconstructing the orbits and understanding the gravity that holds them. These journeys, spanning tens of thousands of AU, reveal the sun's dominion over the outermost reaches. The sun is not distant from these icy worlds. It is their anchor, shaping motion over scales that dwarf human comprehension. Even with modern telescopes, the Oort cloud is nearly invisible. Direct observation is difficult because the objects are faint, small, and far away. But every piece of evidence, from comet trajectories to orbital modeling, points to a massive gravitationally bound shell. Gravity here is subtle but undeniable, acting over incredible distances to trap objects in the sun's sphere of influence. Human attempts to escape, early spacecraft. When humanity first sent objects beyond Earth, the dream was simple: reach for the stars. Yet even with our most powerful rockets, the sun's gravity waits, invisible but unyielding, ready to pull anything back into its grasp. The early spacecraft launched into the outer solar system were the first test of our ability to challenge this immense force. Pioneer 10, launched in 1972, was humanity's first emissary to the outer planets. It was small, a modest spacecraft, with a gold plaque carrying messages for any beings it might meet in the void. Its goal was to fly past Jupiter, study the planet, and continue outward. But from the moment it left Earth, it was tethered. The sun's gravity exerted a constant pull, shaping its trajectory, slowing its departure, and ensuring that, even as it moved into interstellar space, it would remain part of the sun's extended influence for millennia. Pioneer 10's journey demonstrated the limits of human technology against natural forces. After launch, it accelerated away from Earth, passing through the inner solar system with ease. Yet as it left the orbit of Mars and approached the asteroid belt, the sun's pull became noticeable. Calculations had to account for the sun's gravity with extreme precision. Even a small misalignment in the launch angle could have sent it off course, sending the spacecraft into the sun, or leaving it stranded in a slow spiral toward the outer planets. The sun's gravity is patient and unrelenting. Even after millions of kilometers, Pioneer 10 was still being tugged, its motion shaped by the invisible mass at the center of our solar system. Voyager 1 and Voyager 2, launched in 1977, followed shortly after. These spacecraft were built to last, designed to explore Jupiter, Saturn, and for Voyager 2, Uranus and Neptune. But their missions also carried the deeper purpose of testing whether human-made objects could truly leave the solar system. To escape the sun's grip, these spacecraft had to move faster than anything previously launched. Yet even at tens of kilometers per second, they were still prisoners of the sun's gravitational pull. Every maneuver, every trajectory correction was carefully calculated to account for the invisible leash that bound them to the star. The Voyagers relied on a technique known as planetary slingshots, or gravity assists, to achieve the velocities necessary to reach the outer solar system. This method uses the motion and gravity of a planet to accelerate a spacecraft without burning extra fuel. By carefully flying near Jupiter, Saturn, and in Voyager 2's case, Uranus and Neptune, the spacecraft could steal a tiny fraction of the planet's orbital momentum. Each encounter boosted their speed, bending their paths outward and allowing them to travel faster than they could with rockets alone. Yet even these slingshots were not enough to escape the Sun entirely. The Sun's mass dominates, and its gravity shapes the paths of even the fastest human-made objects. Voyager 1, currently the fastest spacecraft ever built by humans, travels at approximately 17 kilometers per second relative to the Sun. That is fast, nearly 40 times faster than Earth's orbit around the Sun. But it is still not enough to break free in the sense of leaving the Sun's gravitational influence completely. The Sun's gravity reaches far beyond the planets, extending past the Kuiper Belt and into the distant regions of the Oort cloud. Voyager 1 is moving outward, yes, but it is still tethered, its path a slow escape from the well it was born within. Voyager 2, slightly slower at about 15 kilometers per second, follows a similar trajectory. Its journey took it past the outer planets in a rare alignment, which allowed it to visit Uranus and Neptune. Each planetary flyby was precisely timed, calculated to maximize the velocity boost and redirect the spacecraft's path. The Sun's gravity had to be considered at every step, influencing the shape of each maneuver, dictating how close the spacecraft could approach a planet and how it would continue onward. Without accounting for the Sun's pull, these missions would have failed, leaving the Voyagers stranded or sent careening into the cold void of space. Pioneer 10, Voyager 1 and Voyager 2 also reveal something profound about our limitations. Despite their incredible speeds, these objects are moving within the Sun's gravitational well. They will never truly escape, in the sense of leaving the star's influence entirely. Even after billions of years, the Sun's mass, though tiny in its effect at these distances, continues to define their motion. The Sun's gravity acts over immense scales, stretching millions of kilometers beyond the last planet, guiding and controlling paths even for objects moving faster than most humans can comprehend. The trajectories of these spacecraft illustrate the invisible architecture of the solar system. Every planetary flyby was a step along a path dictated not by chance, but by the combination of orbital mechanics and the Sun's relentless pull. Pioneer 10 and the Voyagers did not simply travel outward into space. They navigated a complex gravitational landscape shaped by the Sun, planets, and even distant moons. Gravity acts as both a tether and a guide, shaping motion in ways that are subtle but unavoidable. Without this understanding, escape attempts would have been impossible. Pioneer 10 passed Jupiter in 1973, using the planet's gravity to redirect its path outward. This was humanity's first encounter with the delicate balance required to navigate the solar system. Every instrument on board, every signal sent back to Earth, depended on the spacecraft following a path precisely aligned with the combined gravitational pulls of the Sun and Jupiter. Voyager 1 and Voyager 2 took this principle further, planning multi-planet encounters years in advance. Each trajectory was calculated down to the meter, a choreography dictated by the star at the center of the solar system. Even after leaving the planetary region, these spacecraft remain under the Sun's influence. Voyager 1 crossed the heliopause, the boundary where the solar wind meets interstellar space, but it is still moving through the Sun's gravitational field. Its speed, relative to surrounding stars, will eventually allow it to drift into interstellar space, but it will remain, in a sense, forever part of the Sun's extended gravitational domain. Pioneer 10, on a slightly slower path, will take tens of thousands of years to reach comparable distances. The Sun's influence is a slow, persistent tether, shaping trajectories long after the spacecraft have passed beyond planets. Gravity assists themselves are a testament to human ingenuity in dealing with the Sun's pull. A spacecraft approaching Jupiter does not simply fly by. It enters a carefully calculated orbit around the planet's gravity, steals energy from the planet's motion, and exits with a new speed and direction. Each maneuver must account for the Sun's constant tug. Too close, and the spacecraft could be pulled inward. Too far, and the acceleration would be insufficient. The Sun defines the limits of every trajectory, even while planets provide temporary boosts. The early spacecraft also reveal the scale of the solar system's gravitational reach. Distances measured in astronomical units become meaningful only in the context of the Sun's mass. Voyager 1 has traveled over 150 AU since its launch, yet it remains subject to the Sun's influence. At this distance, gravity is weak, almost imperceptible, but it is never zero. Pioneer 10, Voyager 1, and Voyager 2 all show that leaving Earth is easy compared to leaving the solar system. Even the fastest human-made objects must contend with the Sun's reach for thousands of years before they can approach true freedom. The design of these spacecraft reflects the challenge of escaping gravity. They carry minimal fuel for trajectory adjustments because the primary acceleration comes from planetary slingshots. Every gram, every maneuver is calculated to maximize speed while staying within the Sun's gravitational well. Engineers designed them for a journey that would last decades, knowing that the Sun's mass dominates motion far beyond the planets. These missions are not just scientific achievements, they are demonstrations of humanity's attempt to contend with one of the largest forces we can never leave behind. Even after decades in space, these early spacecraft continue to communicate, sending data across billions of kilometers. The signals they transmit follow curved paths influenced by the Sun's mass. Radio engineers must account for this effect, correcting for the Sun's gravity when receiving transmissions. Gravity, it seems, is unavoidable. It reaches even across the empty expanse of interstellar space, bending both matter and signals, influencing everything humanity sends into the cosmos. Pioneer 10 was the first step. Voyager 1 and 2 expanded the reach, traveling farther, faster, and longer. Every encounter with a planet was a calculated gamble, balancing speed against the Sun's unyielding pull. Gravity dictated the allowable paths, the timing of maneuvers, and the energy needed to continue outward. Even in the void beyond Pluto, the Sun's presence is felt, shaping the trajectories of these spacecraft in ways that will persist for tens of thousands of years. The lessons from these missions are clear. Speed alone is insufficient. Even traveling at tens of kilometers per second, the Sun's gravity remains dominant. The Sun is a well that stretches across the solar system, and escaping it is not simply a matter of firing rockets. Humanity's first emissaries show that the farther you go, the longer gravity tugs, the slower freedom arrives. The Sun defines the paths, speeds, and limits of every journey, holding the fastest objects we have ever built in a gentle but persistent grip. Pioneer 10, Voyager 1 and Voyager 2 each followed unique paths shaped by planetary interactions, but all share the same truth. The Sun's gravitational influence is inescapable on a human timescale. Their motion through space demonstrates the limits of propulsion, the power of gravity, and the clever ways we can manipulate motion to extend reach. Each slingshot, each flyby, each maneuver is a battle with the Sun's mass, showing that even with advanced technology, our ability to leave the solar system is bound by natural forces. Modern missions, reaching beyond the Sun's grasp. After the first human-made objects ventured into the outer solar system, humanity did not stop. The dream of escaping the Sun's grasp evolved into precision missions with cutting-edge technology. The New Horizons spacecraft, launched in 2006, was designed to explore Pluto, the Kuiper Belt, and beyond. Unlike the early Pioneer and Voyager probes, New Horizons combined speed, advanced instruments, and modern trajectory planning to push farther and faster. Its journey past Jupiter provided a gravity assist, a borrowed boost of speed, which accelerated it toward Pluto. Every kilometer traveled beyond the planets was a contest against the Sun's invisible pull. The farther New Horizons traveled, the slower the Sun's gravity tugged, yet it was never absent. Even in the distant Kuiper Belt, New Horizons remained tethered, moving along a path defined by the star at the center of the solar system. Gravity still dictated everything. Mission planners accounted for subtle nudges from planets, but the Sun remained the dominant force. New Horizons' speed was impressive, approximately 16 kilometers per second after leaving Jupiter's influence, fast enough to outrun the planets. but not enough to fully escape the Sun's reach. The spacecraft's trajectory into the Kuiper Belt revealed the vast scale of the solar system's gravitational well. Even at billions of kilometers away, the Sun's influence stretches like invisible arms, subtly shaping motion and defining the boundaries of travel. Closer to home, missions like the Parker Solar Probe are rewriting our understanding of both the Sun and the challenges of propulsion. Launched in 2018, Parker Solar Probe is designed to approach the Sun closer than any spacecraft before it, venturing into the corona at speeds of nearly 200 kilometers per second during perihelion. This mission is less about escaping the solar system and more about testing the limits of spacecraft in extreme gravity and heat, but it indirectly shows how powerful the Sun's pull is. Even at the point of closest approach, where speeds are highest, the Sun's gravity is not a distant force. It is the central actor, shaping orbits, guiding motion, and dictating trajectory with precision that cannot be ignored. The Solar Orbiter, launched in 2020, adds another dimension. Its mission combines solar observation with unique orbital mechanics. By approaching the Sun closely and using repeated Venus and Earth flybys, it adjusts its path in ways that stretch the boundaries of traditional mission design. Gravity assists here are not just tricks, they are necessities. Every slingshot, every maneuver uses planetary motion to overcome the Sun's pull, showing that even with modern technology, humans remain within a gravity well that dominates the solar system. Innovative propulsion has become a key part of modern attempts to leave the Sun's grip. Ion drives, for example, provide slow but continuous acceleration, allowing spacecraft to gradually build speed over years. The Dawn spacecraft used this method to explore Vesta and Ceres in the asteroid belt. Unlike chemical rockets that burn quickly and lose force once fuel runs out, ion drives operate for long durations, steadily increasing velocity and extending reach. Yet even with this persistent push, the Sun's gravity remains a constant factor, shaping every trajectory and setting limits on how far and how fast a spacecraft can travel. Solar sails offer a different approach. By using the pressure of sunlight itself to push a spacecraft, solar sails turn the Sun into a propulsion system while simultaneously remaining trapped within its gravity. Acceleration is slow but cumulative, potentially allowing spacecraft to reach velocities sufficient to exit the solar system over decades or centuries. But even here, mission designers must carefully account for the Sun's pull. Trajectories must balance the outward push of light with the inward tug of mass, a dance of energy and gravity that defines motion on a cosmic scale. Despite these innovations, escaping the solar system remains extraordinarily difficult. The energy required to break free from the Sun is immense. To leave the gravitational well entirely, a spacecraft must reach a velocity exceeding the escape velocity at its current position. For a craft near Earth, this is approximately 618 kilometers per second if measured directly at Earth's orbit. No current human-made spacecraft can achieve that speed with chemical or even ion propulsion alone. The energy requirements are astronomical, far beyond what current propulsion systems can provide. Theoretical technologies offer glimpses of what might be possible. Fusion propulsion, for instance, could generate continuous thrust far exceeding chemical rockets. By burning small amounts of fuel with enormous energy efficiency, a fusion-powered spacecraft might accelerate for years, gradually climbing out of the Sun's gravity well. Antimatter propulsion is even more extreme, potentially converting mass directly into energy with near-perfect efficiency. A spacecraft using antimatter could reach speeds approaching a significant fraction of the speed of light, theoretically enabling solar system escape in practical timescales. But these technologies are speculative. They exist in laboratories, on paper, or in simulations, not yet in spacecraft that humans can launch. Current technology forces a trade-off: speed versus mass. The more fuel a spacecraft carries, the heavier it is, and the harder it is to accelerate. Slingshots and ion drives mitigate some of this, but there are limits. The Sun's gravity does not weaken quickly enough for humanity's fastest probes to break free entirely. Each increment of velocity is paid for with ingenuity, precise trajectory planning, and sometimes decades of patient travel. Even with the best propulsion systems today, a spacecraft leaving Earth is starting a journey that, while outward bound, will remain tied to the Sun for millennia. Modern missions also highlight the importance of trajectory precision. A slight miscalculation near Jupiter, Saturn, or even Earth can reduce the effectiveness of a gravity assist, leaving the spacecraft trapped in a slower path or sending it on an orbit that will never reach the outer solar system. The Sun's gravity dominates these calculations. It is not merely a source of light or heat, it is a central force that governs motion over billions of kilometers. New Horizons, Parker Solar Probe, and Solar Orbiter all demonstrate this reality. Each spacecraft moves outward, but the Sun's influence stretches far beyond the planets, shaping every motion, every acceleration, and every orbit. Even missions that do not leave the solar system entirely show the limits imposed by gravity. Parker Solar Probe's repeated dives into the corona demonstrate that as you approach the Sun, escape becomes exponentially more difficult. The closer a spacecraft is to the Sun, the faster it must travel to overcome the increasing pull of gravity. Trajectory corrections, heat shields, and precise orbital timing all interact with the Sun's mass to define what is possible. Spacecraft do not simply move in straight lines, they are navigating invisible curves in space-time, paths dictated by gravity that have existed for billions of years. The challenge of solar system escape extends beyond speed. Spacecraft must survive radiation, micrometeoroid impacts, and extreme temperature gradients. Every maneuver to escape requires careful balance between energy, protection, and timing. Ion drives must operate for years without interruption. Solar sails must remain properly oriented to maintain acceleration. These technical demands exist because gravity is not forgiving. The Sun's pull continues indefinitely, requiring precision and persistence over long durations. Even a small misalignment could result in failure to escape, leaving the spacecraft trapped in a slow spiral back toward the inner solar system. Future missions will need to combine these techniques. Slingshots, ion drives, and solar sails may work together to gradually approach the theoretical escape velocity. Interstellar probes will have to carefully plan trajectories decades in advance, taking into account planetary positions, gravitational assists, and even perturbations from other stars or galactic tides. Every step must account for the Sun's mass, the invisible force that binds the solar system together. Energy must be balanced against velocity, and engineering precision must counteract the subtle but relentless tug of gravity. Even with ideal propulsion, the energy demands are staggering. Chemical rockets, ion drives, and solar sails have limitations in thrust and acceleration. Fusion or antimatter propulsion could overcome these barriers, but these systems face enormous engineering challenges, from fuel storage to energy conversion and safety. The Sun's gravity is constant, unyielding, and absolute. To reach a point where a spacecraft is free of the Sun's pull requires sustained acceleration over decades or centuries, energy beyond what humanity currently produces, and precision beyond what has been achieved. Modern missions like New Horizons reveal the first glimpses of this reality. After passing Pluto, it continues outward into the Kuiper Belt at incredible speed, yet it remains within the Sun's gravitational influence. Even when moving billions of kilometers away, every calculation, every adjustment, every signal sent back to Earth accounts for gravity. Parker Solar Probe and Solar Orbiter, closer to the Sun, illustrate the opposite extreme, approaching a gravity source that is overwhelmingly strong, demonstrating how much energy is required just to maintain orbit or alter trajectory. Together, these missions map the spectrum of human attempts to contend with the Sun's mass, from the slow climb from distant orbits to near-daring plunges into the corona. Gravity wells in a cosmic context. Gravity is everywhere. It is the invisible hand that shapes the motion of planets, stars, and galaxies. But not all gravity is the same. The Sun's gravity is far stronger than Earth's, and Jupiter's gravity is a heavyweight among planets, yet tiny compared to the Sun. Even more extreme, black holes twist space-time into a well so deep that nothing, not even light, can escape. To understand why humanity remains trapped within the sun's influence, we need to explore gravity wells across the cosmos and see how they compare. Imagine standing on Earth. Gravity pulls you downward with a force that is constant, familiar, and predictable. Escape velocity here is about 11 kilometers per second. That means any object, whether a rocket or a baseball, must reach that speed to break free of Earth's pull without further propulsion. For humans, this is already difficult. Rockets must generate tremendous thrust to push through Earth's atmosphere and accelerate past 11 kilometers per s. Even here, the well is relatively shallow compared to the Sun. Earth's mass curves space-time slightly, but it is nothing compared to the solar mass lurking at the center of the solar system. Jupiter, however, tells a different story. Its mass is over 300 times that of Earth, and its gravity is far stronger. Its escape velocity at the cloud tops is roughly 60 kilometers per second. That is over 5 times higher than Earth. A spacecraft approaching Jupiter must contend with this immense pull. This is why the giant planet is so useful for gravity assists. By flying close, a spacecraft can borrow momentum from Jupiter, gaining speed to move outward against the Sun's gravity. But even Jupiter, despite its size, is only a stepping stone. Its well is deep locally, but it is small in the cosmic sense. The Sun's mass dominates the entire solar system, creating a well so deep that escaping it entirely requires velocities many times higher than even Jupiter's escape speed. The Sun's gravity well is the baseline against which all other wells are measured. At Earth's orbit, escape velocity is around 618 kilometers per second. That is roughly 55 times higher than Earth's escape speed. To leave the Sun's influence, a spacecraft must overcome the energy of a mass that is almost 2x 11030 kilograms. Every planet, every moon, every spacecraft within the solar system exists within this well. Even the fastest human-made object, Voyager 1, moving at 17 kilometers per second relative to the Sun, is still trapped. It moves outward, yes, but the Sun's gravitational pull extends far beyond the orbit of Neptune and even into the Oort cloud. The Sun's well is broad, deep, and inescapable without extreme energy. Gravity wells are not only about speed, they define motion. A planet orbiting the Sun moves not because it is trying to escape, but because the Sun's mass shapes a curved path in spacetime. Earth circles at roughly 30 kilometers per second, perfectly balanced between inertia and gravity. Jupiter moves slower relative to the Sun at 13 kilometers per s, yet its mass bends space more strongly, keeping its moons locked in intricate orbits. The deeper the well, the higher the velocities required to escape. This principle explains why the Sun dominates the solar system. Its mass and resulting gravity well are orders of magnitude greater than any planet. Black holes are the ultimate expression of a gravity well. Where Earth's well is shallow and Jupiter's is deep, a black hole's well twists space-time into a singularity. Near a black hole, escape velocity reaches the speed of light. Not even light can leave once it crosses the event horizon. While the Sun's well is vast, it is shallow compared to a black hole. The Sun can trap planets, comets, and spacecraft, but light itself can escape, allowing us to see the Sun's heat and glow across billions of kilometers. Black holes, in contrast, trap everything. They are the ultimate cosmic prisons, demonstrating what gravity can do when mass is concentrated to extremes. Comparing Earth, Jupiter, the Sun, and black holes also shows the spectrum of human challenge. Leaving Earth is possible with chemical rockets. Escaping Jupiter requires more energy, beyond human capability for manned missions. Leaving the Sun is orders of magnitude harder, requiring long-term planning, gravity assists, or theoretical propulsion like fusion or antimatter. A black hole's escape is, with current physics, impossible. Humanity's early probes, New Horizons, and Parker Solar Probe are all examples of navigating gravity wells, each successively deeper and more demanding. The concept of a gravity well also defines the energy landscape of the solar system. Every spacecraft must climb out of a local well, Earth's first, then the Sun's. Every maneuver uses energy to counteract gravity, to overcome the mass that bends space-time. Even the giant planets, which can provide boosts, exist within the Sun's well. They can redirect and accelerate spacecraft, but they cannot free them entirely. The Sun's mass dominates the energy budget of any escape attempt. The Sun's well is not uniform. Its gravity decreases with distance, following the inverse square law. Near Mercury, Venus and Earth, it is strong. At Neptune, it is weaker, but still significant. Beyond the Kuiper belt and into the Oort cloud, it is faint, almost a whisper, yet persistent. Objects in these regions move slowly, sometimes taking millions of years to orbit, yet they remain tethered. Even interstellar objects like Oumuamua pass through, influenced by the Sun's gravity during their brief encounters. The Sun's well extends far, shaping motion across light years. Gravity wells also define trajectories. Voyager 1 and 2 had to carefully navigate not only Earth's and the planet's wells, but the Sun's dominant well. Each trajectory, each flyby, relied on precise calculations to use local gravity to gain speed while moving outward. Without understanding the Sun's well, escape attempts would fail. Spacecraft would either spiral back inward or be deflected into useless orbits. The Sun's gravity well is both a trap and a guide, shaping motion across the entire solar system. Even planets themselves demonstrate the power of wells. Jupiter's moons orbit in precise patterns because of its gravity. The Sun's mass keeps Jupiter in place, preventing it from drifting into interstellar space. Earth's orbit, the orbits of comets, and the paths of asteroids all exist within these nested wells. Gravity wells stack like layers. Earth's local well sits inside the Sun's global well, while Jupiter's deep gravity well exists as a satellite inside the Sun's dominant mass. Spacecraft must navigate these layers to reach targets or achieve escape. The energy required to climb wells is immense. Escape velocity is not just a speed, it is a measure of energy per mass. For the Sun, reaching 618 km per s at Earth's orbit requires enormous kinetic energy. Chemical rockets cannot achieve that in a single boost. That is why interplanetary missions rely on slingshots, ion drives, and solar sails, slowly accumulating speed to climb the Sun's well over decades. The well shapes strategy, dictating how missions are designed and executed. Black holes amplify this lesson. Near a black hole, the well is so steep that all motion is dictated by gravity. Time slows, space bends, and nothing can leave once past the event horizon. Studying these extreme wells helps us understand the Sun's well by contrast. While the Sun cannot trap light, it defines a massive zone of influence. Black holes push this to the extreme, showing the cosmic end of the spectrum. Even theoretically, leaving a Sun-like star requires sustained energy. Current technology allows gradual escape through planetary assists or continuous propulsion. Ion drives, solar sails, and future fusion engines may provide enough acceleration, but the Sun's well ensures that escape is never instantaneous. Spacecraft move slowly outward, constantly feeling the pull of the star. Time and energy dominate every maneuver. The well is the invisible reality of the solar system, defining the boundaries of motion and the limits of human reach. Planetary comparisons illustrate scale. Earth is small, a hill in the cosmic landscape. Jupiter is a mountain. The Sun is a continent, and black holes are a chasm. Climbing out of Earth is possible for humans. Climbing out of the Sun takes decades or centuries with current technology. Approaching a black hole requires speeds impossible to achieve. Gravity wells define what motion is possible, what energy is required, and how objects, natural or human-made, move in space. Even distant spacecraft like New Horizons and Voyager 1 provide a living demonstration. They move outward, yet their motion is shaped by nested wells. Each slingshot, each acceleration, each careful calculation is a response to these wells. Gravity is the silent architect, creating invisible slopes in space-time, sculpting trajectories across billions of kilometers. Every mission, every calculation exists within this layered architecture. Understanding wells is also key to future exploration. Advanced propulsion will allow faster climbs, but the principle remains. Escape is energy intensive. Solar sails can gradually accumulate speed, ion drives can push steadily, and fusion engines may someday provide enough thrust. Yet the Sun's mass continues to define the challenge. Wells are not abstract. They are tangible, persistent, shaping motion for anything leaving Earth, the planets, or even the Kuiper Belt. Black holes remind us of the extreme end. While spacecraft are trapped in the Sun's well for thousands or millions of years, a black hole creates a permanent trap. It bends light, stretches time, and defines a region where motion ceases to be simple. This comparison shows the spectrum of gravitational traps, from Earth's shallow pull through Jupiter's deep local well to the Sun's massive solar system-wide well, up to the ultimate trap of black holes. Humanity is somewhere along this spectrum, grappling with a well that is vast but not infinite, shaping every attempt to leave, explore, and move outward. Even at vast distances, gravity wells shape the motion of comets, asteroids, and interstellar objects. The Sun's influence extends across tens of thousands of AU, interacting with passing stars and galactic tides. Objects at these distances may move slowly, yet they remain trapped. The depth and width of the well define motion, potential escape, and the energy needed to climb out. Comparisons across the solar system, from Earth to black holes, reveal how gravity wells govern the cosmic stage. Every mission, from early probes to modern spacecraft, must navigate these wells. The Sun's gravity dominates, Jupiter's assists provide boosts, Earth's local gravity provides launch challenges, and extreme wells like black holes remain unreachable. Motion is dictated by the interplay of energy, mass, and gravity, showing that the cosmic landscape is shaped not just by objects, but by the invisible wells in which they move. Why the Sun's gravity well is special. The Sun is more than just a bright disk in the sky. It is the invisible anchor of the solar system, the central mass whose gravity binds everything from Mercury to the icy bodies of the Oort cloud. Its gravity well is immense, a vast depression in space-time that stretches billions of kilometers. Unlike Earth or Jupiter, whose gravitational influence is limited to local regions, the Sun dominates the entire solar system. It sets the rules of motion for planets, comets, asteroids, and even the fastest human-made spacecraft. The well is broad, deep, and unyielding. To understand its uniqueness, consider the speed required to leave its grasp. Earth's escape velocity is around 11 kilometers per second. Jupiter's is about 60 kilometers per second. The Sun, at Earth's distance, requires 618 kilometers per second. That is a velocity so high that every spacecraft humanity has ever built falls short by an order of magnitude. Pioneer 10, Voyager 1 and 2, New Horizons. They all move at tens of kilometers per second. Fast in human terms, but painfully slow relative to the Sun's gravitational pull. Even as they move outward towards interstellar space, they remain bound, moving through the Sun's massive field for thousands or even millions of years. The Sun's gravity well is unique because it is both deep and wide, deep enough to tether objects even at vast distances, yet wide enough that it dominates the motion of planets and comets alike. Mercury zips around in a close, tight orbit because of the Sun's strong pull. Neptune drifts slowly along the edge of the planetary zone, still obedient to the Sun's tug. Comets from the Kuiper Belt and icy bodies from the Oort cloud trace paths dictated by the Sun's gravity, barely moving relative to its influence, yet never escaping entirely. This reach across the solar system is unmatched by any other object. Jupiter, despite its mass, only dominates a local region. The Sun's influence stretches across light hours, capturing everything within its sphere of dominance. Even human ingenuity struggles against this force. Voyager 1, traveling faster than any spacecraft before it, will not truly escape the Sun for tens of thousands of years. Its speed of about 17 kilometers per second is dwarfed by the energy required to climb completely out of the Sun's well. New Horizons, launched faster than most, relied on a gravity assist from Jupiter to even approach the outer solar system with any hope of continuing onward. Every mission beyond the planets must carefully navigate the Sun's invisible slopes, using ingenuity and precision to accumulate enough energy to move outward. The Sun's gravity well is not just a local challenge, it is a universal roadblock for interstellar travel. Attempting to reach the nearest star, Proxima Centauri, presents a vastly more daunting challenge than simply leaving the solar system. Even if a spacecraft could achieve escape velocity from the Sun, it would still need to accelerate further to cross the gap of 4.24 light-years. The Sun's gravity sets the starting point, a massive energy barrier that must first be overcome before interstellar distances can be addressed. Every interstellar journey begins with a climb out of this solar well. The scale of the Sun's influence becomes clearer when comparing distances. Voyager 1 is over 150 astronomical units from the Sun, yet it remains bound. The escape velocity at that distance is lower than at Earth's orbit, but still significant. The solar system is not empty space. It is a vast gravity well whose edges are defined by tens of thousands of AU. Objects in the Oort cloud move slowly, often taking millions of years to complete an orbit, yet they remain gravitationally tethered. The Sun's well is not a simple sphere. It stretches into the interstellar medium, interacting with galactic tides and passing stars, still defining motion over vast distances. Modern propulsion systems illuminate the challenge further. Ion drives provide small but continuous thrust, gradually pushing spacecraft outward, yet they still operate within the Sun's massive gravitational influence. Solar sails harness light for acceleration, but even the Sun's photons, powerful as they are, cannot provide instantaneous escape. The Sun's mass dictates that speed alone is not sufficient. Energy must be carefully accumulated over time. Slingshots around Jupiter or Saturn provide temporary boosts, but these planetary assists exist within the Sun's larger well. There is no way to bypass it. Every maneuver, every acceleration, every trajectory is shaped by the central star. Interstellar travel highlights the Sun's role as both barrier and starting point. Even a hypothetical spacecraft traveling at 10% of the speed of light would need to first escape the solar system. The energy required to reach this velocity from Earth's orbit is immense, because it must overcome the Sun's gravity while accelerating further into the void. The Sun's well is the first and largest hurdle for any interstellar mission. Its depth and breadth set the energy scale for human exploration beyond our solar neighborhood. Gravity assists demonstrate the Sun's significance indirectly. Voyager 2 used the alignment of the outer planets to gain velocity, yet each maneuver had to account for the Sun's gravitational field. Jupiter's assist increased speed, Saturn's adjusted trajectory, Uranus and Neptune contributed additional boosts. Without these calculations, the spacecraft would have remained trapped in the Sun's well, unable to progress outward. The Sun's pull dominates even when we attempt to exploit planetary motion to escape. Even for robotic missions, the Sun's gravity imposes constraints on mission design. Spacecraft must carry fuel for trajectory corrections, maintain communication with Earth over billions of kilometers, and withstand long travel times. The energy budget is dictated by the depth of the solar well. A trajectory miscalculation can result in failure to escape, even if the craft is moving faster than any previous mission. Escape is not just a matter of speed, it is a careful negotiation with the Sun's immense mass. Interstellar implications extend to planning and engineering. Proxima Centauri, 4.24 light-years away, is a distant target. Even leaving the Sun's well is only the first step. A spacecraft must maintain acceleration, avoid obstacles like interstellar dust, and remain on a precise trajectory across the vast emptiness. The Sun's gravity defines the starting conditions. If energy is insufficient to climb out of the solar well efficiently, the journey becomes exponentially more difficult. The Sun is both the anchor and the first barrier for any voyage beyond the solar system. Advanced propulsion concepts are considered to overcome this barrier. Fusion engines, which generate continuous thrust over years, might allow spacecraft to steadily climb out of the Sun's well while accelerating toward interstellar targets. Antimatter propulsion, theoretically converting mass entirely to energy, could provide velocities sufficient to escape the Sun and reach nearby stars within decades. Yet even these hypothetical engines must contend with the Sun's mass. Escape from the solar system is never instantaneous. It is a process of accumulating energy, precisely managing acceleration, and navigating the central gravitational field. The Sun's well is not uniform. It diminishes with distance, but never disappears. At Earth, the escape velocity is extreme. At Neptune, it is lower, yet still significant. In the Oort cloud, gravity is faint but persistent. Even hypothetical interstellar probes must account for this pull over years or decades of travel. The Sun shapes motion over enormous scales, making its gravity well the defining feature of the solar system. No planet, no comet, and no spacecraft can ignore it. Observations of interstellar objects passing through the solar system, such as Oumuamua, show the Sun's influence at work. These objects, moving at high speeds relative to the Sun, are still subtly deflected, their paths altered by the Sun's gravity. Even for objects not bound to the solar system, a close approach to the Sun changes trajectories. This demonstrates how pervasive the Sun's well is. It reaches beyond the planets, beyond the Kuiper belt, and shapes motion even for transient visitors. The Sun's well also interacts with galactic forces. Nearby stars, galactic tides, and the motion of the Milky Way itself all influence objects in the solar system, but the Sun remains the central mass. Interstellar travel must start with this well as the reference point. Without escaping it, motion toward other stars is impossible. The energy required to leave the Sun is the baseline for any interstellar journey. Even theoretical missions traveling at significant fractions of light speed begin within the Sun's gravitational influence. The Sun's mass dominates the local environment. Early maneuvers, trajectory adjustments, and energy calculations are all performed relative to the Sun's pull. Ignoring this well would render any interstellar plan impossible. It is the cosmic anchor from which all outward motion must be measured. The fastest human-made objects illustrate the scale of the challenge. Voyager 1, moving at 17 kilometers per s, takes tens of thousands of years to escape the Sun's gravitational influence completely. New Horizons, faster at launch, relies on planetary assists, yet it too remains bound for millennia. These spacecraft demonstrate the sheer depth of the Sun's well. Even with careful planning, precise engineering, and decades of travel, leaving the Sun is an enormous task. The Sun's gravity well defines the solar system itself. Planets orbit, comets follow long elliptical paths, and spacecraft must navigate layers of gravitational influence. Escape is not simply about moving away, it is about accumulating energy over time, carefully negotiating the pull of the central mass. The Sun dominates all motion within its reach, from Mercury to the Oort cloud, and defines the energy required to travel outward toward other stars. Interstellar implications extend beyond speed. Navigation, timing, and acceleration all depend on the Sun's gravity. Reaching Proxima Centauri is not simply a matter of pointing a spacecraft in the right direction. The Sun sets the initial conditions. Energy must first be spent to climb out of its well before any journey between stars can begin. This makes the Sun's well the defining obstacle for interstellar exploration. Even with future technologies, the Sun remains a persistent factor. Continuous thrust from ion drives, fusion engines, or solar sails must overcome the Sun's mass over years or decades. Every acceleration is measured relative to the solar gravitational field. The Sun's gravity is both constant and pervasive, dominating motion across billions of kilometers and defining the limits of human travel. The role of gravity in celestial news. The solar system is never static. It is a living, shifting, dynamic system, and gravity is the force choreographing every move. Recent discoveries in astronomy are revealing just how complex and surprising this dance can be. Far beyond the planets and moons we know, scientists are spotting objects on extreme orbits, unexpected visitors from beyond, and even subtle changes caused by solar events, all of which highlight how gravity continues to shape the cosmic stage. One of the most intriguing mysteries of recent years is the search for Planet 9. Astronomers noticed that certain distant objects in the Kuiper belt were moving in unusual ways. Their orbits were tilted, elongated, and clustered in patterns that could not be explained by the gravity of the known planets alone. Something massive, hidden, and far away seemed to be tugging on them. The idea of Planet 9, a hypothetical giant planet lurking tens of billions of kilometers away, emerged. If it exists, it is shaping the orbits of icy bodies at the edge of the solar system, subtly twisting and stretching their paths over millions of years. These extreme orbits are evidence of the Sun's gravitational well interacting with unseen forces, showing that even at the outer edges, motion is dictated by the invisible hand of mass. Then there are interstellar visitors. In 2017, an object named Oumuamua passed through the solar system at incredible speed. Unlike comets or asteroids from the Kuiper belt or Oort cloud, Oumuamua came from another star. Its trajectory was hyperbolic, meaning it was not bound to the Sun's gravity. Yet even as it streaked through, the Sun's pull altered its path slightly, bending its motion, revealing how even brief encounters with a massive star can change the flight of an object moving at tens of kilometers per second. Studying Oumuamua and other fast interstellar objects teaches us about the limits of gravitational capture. Some objects can escape entirely, while others are trapped for millennia, orbiting silently at the edge of the Sun's influence. Recent discoveries are not limited to extreme orbits. Astronomers are also spotting distant icy bodies that seem almost frozen in time, moving slowly at the far reaches of the solar system. Sedna, for example, travels along an incredibly elongated orbit, taking over 11,000 years to complete a single revolution around the Sun. Even at its farthest distance, tens of billions of kilometers away, the Sun's gravity is enough to maintain its orbit. These findings remind us that gravity is not a force that weakens to irrelevance. It is persistent. It stretches across the solar system, binding icy remnants of formation into a slow, measured dance that may last for tens of thousands of years. While the outer reaches of the solar system grab headlines, the Sun itself is far from inactive. Solar flares and coronal mass ejections are dramatic, violent events that hurl plasma and magnetic fields outward at millions of kilometers per hour. These events may seem like weather in space, but they have real effects on motion and trajectories. Spacecraft in orbit or passing through the inner solar system must account for these events. A massive ejection can alter the path of a small object or affect the delicate balance of a spacecraft using solar sails. Gravity remains constant, but the dynamic activity of the Sun adds a layer of complexity. Navigating this environment requires precision, awareness, and technology capable of reacting to sudden changes in force fields. Even fast-moving probes like Parker Solar Probe experience the Sun's influence directly. As it dives into the corona, the Sun's gravity and intense radiation interact, creating complex dynamics. Tiny deviations in trajectory caused by solar events or uneven gravitational gradients can affect mission outcomes. Every approach, every orbital insertion must consider both the steady pull of mass and the variable forces of solar activity. These events, though fleeting on cosmic timescales, can have lasting impacts on spacecraft speed, direction, and energy use. In addition to solar events, planetary interactions continue to make headlines. Astronomers regularly detect objects on odd paths, some seemingly flung from the Kuiper belt, others perturbed by Jupiter, Saturn, or Neptune. These interactions are like a cosmic pinball game, where gravity serves as both flipper and obstacle. One sudden shift can send an icy body toward the inner solar system, where it may become a comet visible from Earth, or hurl it toward interstellar space. Tracking these objects reveals the subtle, persistent role of gravity in shaping motion across millions of kilometers. Even tiny perturbations can have massive consequences over time. One fascinating aspect of recent observations is the interplay between interstellar and solar system dynamics. Objects like Oumuamua and 2I/Borisov demonstrate that stars are not isolated. They exchange matter in fleeting encounters, influenced by the gravity of passing suns. The sun's gravity well stretches far enough to affect these interstellar travelers, bending paths, slowing motion, or sometimes capturing them into long-term orbits. While the well may not hold these objects permanently, it exerts influence sufficient to alter trajectories, proving that gravity reaches beyond the planets and even past the edges of the Kuiper belt. Solar events, interstellar visitors, and extreme orbits all show that gravity is an active player in the cosmic story. Unlike a static backdrop, it shapes motion, energy, and opportunity. For spacecraft attempting interstellar travel, it sets the initial conditions. For distant icy bodies, it maintains the order of their orbits over millennia. For fast interstellar objects, it bends, slows, and occasionally captures. Gravity is the constant amid the changing dynamics of space, weaving all motion into a pattern that can be traced, predicted, and studied. Recent technological advances allow us to see these effects in action. Space telescopes track comets and asteroids with unprecedented precision, revealing subtle shifts in position that hint at unseen mass or interstellar influence. Surveys of the outer solar system are mapping extreme orbits, suggesting the presence of objects like Planet 9. Solar monitoring missions capture flares and mass ejections in real time, helping engineers adjust spacecraft paths. Each discovery reinforces the central role of gravity as the invisible sculptor of motion. Fast-moving interstellar objects provide another narrative. Their hyperbolic trajectories highlight the limits of solar capture. Some, like Oumuamua, pass through without ever being bound. Others might be slowed just enough to become temporary visitors. Studying these objects helps us understand the boundaries of the sun's well, the energy required for capture, and the mechanics of gravitational interaction across light years. Every passing object adds data, a story written in velocity, mass, and distance, revealing the dynamic reach of the sun's gravity. Solar flares and coronal mass ejections add drama to this story. Unlike static gravitational wells, these events introduce forces that fluctuate in intensity and direction. They can accelerate particles to near-light speed, push plasma clouds outward, and create magnetic storms that interact with spacecraft. Even small changes in timing or position can lead to measurable deviations. Gravity dominates the long-term paths, but solar activity adds a chaotic, unpredictable element that must be factored into modern mission planning. The outer solar system continues to produce surprises. Distant objects with extreme orbits, like Sedna and other trans-Neptunian bodies, challenge our understanding of formation and motion. Their elongated paths suggest past encounters, perturbations, or hidden masses influencing the solar system's structure. Gravity is the common thread linking all these phenomena. It is the invisible hand-shaping orbit, deflection, capture, and escape across billions of kilometers. Every new discovery is a reminder that gravity is not merely a force, it is a storyteller. Observing extreme orbits hints at hidden mass. Tracking interstellar visitors exposes the limits of capture. Monitoring solar events demonstrates the influence of dynamic forces. Gravity ties these phenomena together, shaping motion, defining energy budgets, and governing every spacecraft trajectory. The sun's gravity well is the stage, and recent celestial news is the performance, unfolding in real time across the solar system. Even speculative hypotheses like Planet 9 highlight the sun's role. If such a planet exists, it is caught in the sun's well, moving in a slow, deliberate orbit, tugging on distant objects over millions of years. Its unseen mass reveals itself only through gravitational influence. The sun's well allows such structures to exist, organizing motion even when direct observation is impossible. Every calculation, every observation, every trajectory is influenced by this invisible presence. Fast interstellar objects add urgency to this understanding. They demonstrate how energy, velocity, and gravitational interaction define motion. Objects passing through the solar system at tens of kilometers per second are influenced by the Sun's mass, even briefly. Slight deflections, measurable accelerations, and trajectory changes are all dictated by gravitational principles. They provide live examples of how the Sun's well stretches beyond the planets, reaching out to influence objects traveling between stars. Solar events are the unpredictable actors on this stage. Coronal mass ejections can disrupt trajectories, push small objects off course, and create risks for spacecraft. Gravity defines the overall structure of motion, but solar dynamics introduce variability. Space missions must anticipate, adapt, and correct, balancing steady gravitational forces with chaotic bursts of solar activity. Each flare, each ejection, adds a chapter to the unfolding story of motion within the Sun's well. Observations of distant icy bodies, interstellar visitors, and solar activity collectively reveal that gravity is both constant and variable. It is constant in its omnipresence, shaping orbits and dictating energy requirements. It is variable in its interaction with moving masses, dynamic solar events, and interstellar encounters. The Sun's gravity well is the central player, dominating motion while accommodating surprises, weaving a complex, ever-changing narrative across the solar system. The study of these phenomena is not abstract. It informs spacecraft navigation, mission planning, and interstellar ambition. Every trajectory calculation considers the Sun's well. Every correction accounts for gravity. Every mission is constrained by the energy needed to escape. Extreme orbits and fast interstellar objects are not just curiosities, they are proof of the Sun's gravitational influence stretching across the cosmic neighborhood. Even subtle gravitational effects matter. Long-period comets from the Oort cloud, minor deviations in asteroid paths, and interstellar objects passing at high speed are all shaped by mass distribution, planetary alignment, and the central pull of the Sun. Observing and modeling these effects allow us to predict motion, plan missions, and understand the architecture of the solar system. The Sun's well is the framework upon which these stories are written, the invisible stage for a performance that spans billions of kilometers. Breaking the Sun's grip. The Sun's gravity well is vast, deep, and relentless. Every planet, moon, and spacecraft in the solar system exists within its reach. Even the fastest human-made objects, Voyager 1, New Horizons, Parker Solar Probe, struggle to climb out. The energy required is immense, and the journey outward is measured not in years, but in decades or even millennia. Yet human ingenuity has never been content to simply orbit within bounds. For centuries, we have dreamed of leaving the Sun's grip entirely, venturing into interstellar space. While the challenge is daunting, scientists and engineers have imagined methods, both current and speculative, that could eventually allow us to escape. One of the first and most practical methods is the planetary flyby, also known as a gravity assist. This technique relies on the mass and motion of a planet to provide a slingshot effect. A spacecraft approaching a massive planet like Jupiter can accelerate dramatically without expending additional fuel. The planet's gravity bends the spacecraft's trajectory, transferring momentum from the planet's orbital motion to the spacecraft itself. Each flyby must be timed with incredible precision. Even minor miscalculations can result in missed windows, wasted energy, or trajectories that return the craft toward the Sun rather than away from it. Gravity assists are already part of our history of exploring the outer solar system. Voyager 2 famously used a grand tour of the outer planets, leveraging their mass to gain speed. Every maneuver was carefully calculated to maximize acceleration while navigating the Sun's immense gravitational well. New Horizons, on its journey to Pluto and beyond, relied on Jupiter's boost to increase speed by over 4 kilometers per second, a substantial gain in the cosmic scale. These examples demonstrate that even within the Sun's grip, careful exploitation of planetary motion can provide a way outward. Yet planetary flybys have limits. They rely on planets being in the right positions and cannot provide infinite acceleration. To truly escape the Sun's well, more advanced concepts are necessary. One such idea is the solar sail. A solar sail harnesses the pressure of sunlight itself to generate thrust. Photons have no mass, but they carry momentum. When they reflect off a large reflective sail, they push the spacecraft ever so slightly. Alone, this force is tiny, but over months and years, continuous pressure can gradually accelerate a spacecraft to unprecedented velocities. Unlike chemical rockets, solar sails do not carry fuel, allowing potentially endless acceleration. The concept of solar sails is not merely theoretical. The Japanese Icaros mission successfully demonstrated the principle in 2010, unfurling a thin reflective membrane and using sunlight for propulsion. The craft altered its speed and trajectory subtly but measurably, proving that the Sun itself can become a source of motion. For interstellar ambitions, solar sails could provide a way to gradually climb out of the Sun's deep gravity well. They would not provide instantaneous escape, but over time they could allow a spacecraft to accelerate continuously, slowly freeing itself from the Sun's hold. Beyond solar sails, even more ambitious concepts have been proposed. Laser propulsion envisions using ground-based or orbital lasers to accelerate a lightweight craft. The idea is to focus immense energy on a reflective surface attached to the spacecraft, pushing it with photons far more effectively than natural sunlight. Theoretically, such a system could accelerate small probes to a significant fraction of the speed of light. The Breakthrough Starshot initiative, for example, plans to launch centimeter-scale spacecraft toward Proxima Centauri at 20% of light speed using powerful Earth-based lasers. In this vision, escaping the Sun's gravity well is just the first step. Once free, the craft would continue accelerating across interstellar space, propelled by concentrated beams of light. Even with advanced propulsion, energy requirements remain staggering. The Sun's escape velocity at Earth's orbit is 618 kilometers per second. Achieving this requires enormous energy per kilogram of spacecraft mass. Chemical rockets, the workhorses of the space age, are insufficient. Solar sails and laser propulsion circumvent some of these limitations by providing continuous acceleration over long durations. But the climb out of the Sun's well is slow and deliberate. Every trajectory must account for gravity, orbital momentum, and the positions of planets and moons. Escape is never instantaneous. It is a careful dance with energy and motion. Speculative ideas extend even further. Nuclear propulsion, using either fission or fusion, could provide sustained thrust far exceeding current chemical rockets. A fusion engine might burn hydrogen or helium-3 to produce continuous acceleration, gradually overcoming the Sun's gravity well while propelling a craft toward interstellar destinations. Antimatter propulsion, the theoretical conversion of mass entirely into energy, could provide even higher velocities, potentially sufficient to leave the solar system rapidly. While such technologies remain beyond our current engineering capabilities, they illustrate that the Sun's gravitational well, though immense, is not necessarily insurmountable given sufficient energy and innovation. Even without exotic propulsion, careful trajectory planning allows spacecraft to take advantage of natural forces. The interplanetary medium itself can provide subtle assists. Magnetic fields, solar wind pressure, and radiation gradients can be harnessed to tweak trajectories, conserve energy, and maintain acceleration. These methods require precise understanding of physics, sophisticated guidance systems, and long-term planning. But they provide a way to incrementally escape the Sun's grip. The concept of breaking free is not limited to probes. Hypothetical crewed missions, while far more massive and constrained by human life support, could benefit from the same principles. Gravity assists, solar sails, and continuous propulsion could, in theory, allow humans to leave the solar system, though over decades or centuries rather than months. Every kilogram of mass matters. Every maneuver is calculated to maximize efficiency, to convert energy into velocity, without wasting fuel. The Sun's gravity well sets the stage, dictating the scale of the challenge. Planetary flybys remain central to escape planning. Each planet in the solar system has its own gravity well. Jupiter, with its immense mass, can provide the largest boosts. Saturn, Uranus, and Neptune offer additional opportunities. By carefully sequencing flybys, a spacecraft can gain velocity in steps, each maneuver pushing it further out of the Sun's well. This technique has limits, but it demonstrates the principle that gravity itself can be exploited to break free. The Sun's pull is strong, but with ingenuity it can be turned into an advantage. Even interstellar concepts leverage the Sun directly. The idea of a solar O-berth maneuver proposes diving close to the Sun to take advantage of its gravitational energy. By firing a rocket at perihelion, the spacecraft gains additional speed amplified by the Sun's immense gravitational field. The closer the dive, the more energy gained. This technique combines the Sun's mass with propulsion to maximize escape velocity. It is risky, technologically challenging, and requires extreme heat shielding, but it illustrates the interplay of gravity and energy in achieving interstellar escape. Long-term projects also consider multi-generational missions. Continuous propulsion, such as ion drives powered by nuclear reactors or solar panels, could accelerate a spacecraft over decades. By slowly climbing out of the Sun's well, the craft would eventually reach interstellar space. Speed at launch matters, but sustained acceleration over time allows escape with smaller energy peaks, turning a slow, deliberate climb into a successful departure. The Sun's well dictates the timeline, forcing mission planners to consider years, decades, and even centuries of motion. Speculative technologies like laser sails, antimatter engines, and nuclear propulsion provide glimpses of a future where humans or probes could leave the Sun entirely. Planetary flybys, solar O-berth maneuvers, and continuous acceleration allow us to exploit natural dynamics. Even in the 21st century, we are beginning to understand how to climb this massive gravity well. The Sun dominates, but it can also be part of the solution. Each step, each maneuver, each new technology is designed to convert the Sun's pull into forward motion, gradually transforming a prison into a launch pad. Interstellar escape is also constrained by the Sun's influence on trajectory planning. Even with powerful propulsion, every path must account for the central mass. Slingshots, solar sails, and continuous thrust are all measures designed to overcome this barrier. Without careful calculation, spacecraft risk falling back into the Sun's well or being sent off course entirely. Escape is not instantaneous. It is a long, deliberate process that tests our understanding of physics, engineering, and timing. In all speculative designs, energy is the central challenge. To leave the Sun, a spacecraft must gain enough kinetic energy to overcome the gravitational potential. Planetary assists provide boosts, solar sails provide continuous acceleration, and theoretical engines promise vast power. Each technique addresses the Sun's well in different ways, either by harnessing external momentum, providing gradual thrust, or converting mass into energy. The Sun defines the scale of the challenge, and every solution must reckon with its immense gravity. Even interstellar ambitions toward Proxima Centauri, Alpha Centauri, or more distant stars begin with the same principle. First, escape the Sun. The Sun's gravity well is the starting line. It sets the energy budget, defines trajectories, and dictates mission architecture. Planetary flybys, solar sails, laser propulsion, nuclear engines, and O-berth maneuvers all share a common goal: break free from this dominant central mass. Without overcoming the Sun, interstellar travel remains impossible, no matter how fast the spacecraft could theoretically go once free. Hypothetical high-speed propulsion. For as long as humans have looked at the stars, speed has been the problem. Not direction, not curiosity, but speed. The Sun does not lock us in with walls or chains. It locks us in with energy. To leave the solar system, you do not need permission. You need power, and a lot of it. Chemical rockets were enough to leave Earth, but they were never meant to leave the Sun. So engineers and physicists began asking harder questions. What kind of engine could actually climb out of the sun's gravity well, instead of slowly crawling along its edges? And what kind of propulsion does not just move fast, but keeps moving fast long enough to matter? That question leads to ideas that sound extreme, but are rooted in real physics. Two ideas come up again and again: antimatter rockets and fusion drives. These are not science fiction in the loose sense, but science pushed to its absolute edge. Antimatter is not imaginary. It exists. We make it in particle accelerators, detect it in cosmic rays, and measure it in laboratories. Antimatter is matter's mirror image, the same mass but opposite charge. When antimatter touches normal matter, both vanish. They do not burn, and they do not explode in the usual sense. They convert almost all of their mass directly into energy. That matters because energy is exactly what escaping the sun requires. Chemical rockets convert a tiny fraction of mass into motion. Nuclear fission does better, fusion does better still, and antimatter converts nearly everything. 1 kilogram of antimatter reacting with 1 kilogram of matter releases more energy than the largest nuclear weapon ever built. And that is not a metaphor. It is a number. In theory, an antimatter rocket could produce thrust far beyond anything humanity has ever built. Enough thrust to accelerate continuously, enough thrust to reach speeds that make the sun's gravity look small instead of overwhelming. With enough antimatter, a spacecraft could leave the solar system in years instead of tens of thousands of years. But theory is not engineering. The first problem is production. We can make antimatter, but only in tiny amounts, nanograms at enormous cost. To fuel a spacecraft, you would need grams, then kilograms, each gram requiring energy measured in years of total power output from entire nations. The second problem is storage. Antimatter cannot touch normal matter. Not walls, not containers, not air. It must be suspended using magnetic fields perfectly, because any failure means instant annihilation. And the third problem is control. An antimatter rocket must release energy slowly and precisely. Too fast, and the spacecraft destroys itself. Too slow, and the advantage disappears. Even if these problems were solved, antimatter propulsion faces another challenge. Speed creates danger. At a significant fraction of light speed, dust grains become bullets, and single atoms hit with the force of explosives. The interstellar medium is thin, but at extreme speed, thin is still lethal. Antimatter rockets promise freedom from the sun, but they also introduce risks no spacecraft has ever faced. Fusion is quieter, more patient, more realistic. Fusion powers stars, joining light atoms into heavier ones and releasing energy in the process, and the sun does this constantly. On Earth, we have not mastered controlled fusion yet, but we are closer than ever. Fusion propulsion does not aim for instant escape, it aims for steady power. Instead of one violent burst, a fusion drive would push continuously, day after day, year after year, and that matters because escaping the sun is not about a single push, it is about climbing a hill that never ends. A fusion-powered spacecraft could leave Earth, spiral outward, and keep accelerating the entire time. Not fast at first, but relentless. Over years, speed adds up. Fusion drives could realistically reach tens or even hundreds of kilometers per second. Not enough to ignore the sun, but enough to outlast it. Energy budgets matter here. To leave the solar system in a human lifetime, a spacecraft needs sustained power output far beyond chemical rockets. And fusion offers that, without carrying absurd amounts of fuel. Hydrogen is light, fusion fuel is efficient, and the math works better than any other near-term idea. But fusion propulsion still faces limits. Reactors are heavy, radiation shielding adds mass, and heat must be managed continuously. Even with fusion, escape is slow. A fusion spacecraft might take decades to truly leave the sun behind, still faster than Voyager, but slow compared to human expectations. Fusion is not a sprint, it is a long climb. Energy budgets versus reality. Here is the part that most discussions skip. Energy does not care about ambition. To escape the sun from Earth's distance requires an enormous amount of kinetic energy, and that energy must come from somewhere. Chemical rockets cannot supply it. They burn too quickly and waste too much mass. Ion drives supply energy slowly, but not enough. Fusion could supply enough energy, but only with massive infrastructure. Antimatter supplies more than enough energy, but at a cost that borders on impossible. Humanity's total energy production today is tiny compared to what interstellar escape demands. Not small, tiny. Even a modest antimatter spacecraft would require energy equivalent to decades of global power output just to create the fuel, and fusion would require reactors far beyond anything currently operational. This is not a failure of imagination, it is a statement of scale. The sun's gravity well is not just deep, it is honest, and it demands payment in energy, and it does not accept shortcuts. Escaping the sun is only the first battle, and high-speed travel introduces new enemies. The interstellar medium looks empty, but it is not. It contains atoms, dust grains, magnetic fields, and radiation. At low speeds, these are harmless, but at high speeds, they are deadly. A grain of dust hit at tens of thousands of kilometers per second releases energy like a bomb, and shielding against this requires mass, which increases energy needs. Cosmic rays are another problem. High-energy particles from distant stars and supernovae pass through space constantly, and at high speeds, shielding becomes harder, not easier. Electronics fail, materials degrade, biological tissue suffers damage, and unlike Earth, there is no magnetic field to protect a spacecraft far from the sun. Navigation also becomes harder. At extreme speeds, tiny errors grow fast. A fraction of a degree becomes millions of kilometers off course, and communication delays stretch into years, making corrections impossible. High-speed propulsion solves one problem and creates several others. Antimatter rockets and fusion drives are not fantasies. They are boundaries. They show what physics allows, even if engineering lags behind, and they tell us that escaping the sun is not impossible. It is expensive, it is dangerous, and it is slow. Every calculation points to the same truth. The sun does not trap us with force alone. It traps us with scale. To leave, humanity must become an energy civilization, not just a technological one. And until then, even our boldest propulsion ideas remain sketches on the edge of possibility, staring up at a gravity well that has ruled our motion since the solar system was born.